Some desire of nations bow in one the hearts of all mankind. Oh, be blessed.
Hello, my name is Anastasia and I'm very excited to finally bring you this series where we're going to create procedural lake houses in Houdini, all the way from generating the main silhouette to creating the shaders and placing set dressing. I will show you how to achieve the results you see here by creating a set of rules that is flexible enough to support complex silhouettes and relations, which will allow you to unleash your creativity when it comes to procedural building creation. By the end of the series, you will be able to create the base silhouette, define relationships between various elements, procedurally place modules, generate additional geometry to give the building a finished look, and create all the needed shaders that will be driven by the system. I will walk you through all the core concepts that are used to make this possible, which will give you a good foundation that you can apply in any other project. I will also provide you with all the necessary assets and files you will need for this tutorial. However, I highly recommend you to take this opportunity and create something of your own. I will expect of you to have a good knowledge of Houdini user interface, as well as some basic knowledge of Vex. If you never used Vex before, don't worry, you can still follow this tutorial. Just make sure to check the official documentation in Vex before starting. So that's it for the introduction, and I'm so looking forward to starting this series with you.
Hello and welcome to the first chapter of the tutorial, where we are going to set up a network which will generate the base silhouette of our building, and we will start with the body. The idea behind the body is quite simple. First of all, how do we build something when we do it manually? We always build something in relation with what we already have. So our starting point will be a box, which we will be converting into a point cloud constrained to a grid. So we'll receive points here, on the side, inside as well. And we will use these points to drive the position of the next box by choosing a random one. And that random one will be like a center to the next box. And then we just repeat this process, so this box also gets absolutely the same treatment and drives the next box. And we repeat this process until we have a silhouette that satisfies to our constraints, which we will specify in the Houdini. So let's dive into it. So let's start with creating an origin box and naming it origin box. And it will be the driver for all the following boxes in our system. As for the size, since the system heavily relies on the modular approach, and the module size is 2 by 3 by 2, I found that the numbers 4, 3, and 6 work best for the initial box. Basically means that the initial box is 2 modules wide, 3 in length, and 1 in height. As for the center, we need to make sure that the corner of the box is in the origin of the grid. So it's easily done by copying parameter and pasting relative reference divided by 2. And repeat this process for all the other axes. So axis Y, and the last one. So the next step is we will need a box ID attribute. So let's grab attribute create. Rename it to box ID. So box ID. ID. It should be a class primitive and type integer, so it should start with 0 as well, so all correct. Box is ready now to be in the for each loop. However, first we need to figure out how we're going to convert the box into the grid constrained point cloud. First, we need to grab an ISO offset, which will create a volume out of our box. You might notice that the bounding box of the volume is much bigger than our initial box. All we need to do is increase the sampling and make sure to increase the offset as well so the volume fills all the box, which is important for the scatter node as it scatters based on the density of the fog. So for example, if we go back and we say that this is 0, 5, so something smaller. So you see it will scatter more points where the volume is more dense. So let's put it back. 50, 4. And we don't need so many points, like 400 is more than enough. So now, how do we constrain all these points to the grid? We would need to grab a wrangle node, and let's call it grid. This node will allow us to write a vex code, which is a Houdini expression language. Make sure that it is set to points, which means that this code will be executed for every point that is in the specified input, but in this case we have only one input. So what do we want this code to do? Let me illustrate. So let's first illustrate it only on one axis. So here are our points with some random positions. So let's say that this is 0.1, this is 1.5. So, and we want them only to have the numbers divisible by 2. So 0, 2, 4, 6. And there is a function in vex called rint, which rounds all the numbers to the closest integer. So what will happen is this. But you can see this also have numbers we don't need, like 1 or 3. So how do we avoid those numbers? Well, we take all the original positions and we divide them by the number we need, which is 2 in this case. And only then we round them. And then we multiply them back. So what happened is, like, for example, this number, which is here, usually it would be rounded to oh, actually this is already rounded to, let's say, another one, like this one, yeah. So this one, which is here, originally it was rounded to 1. However, when we divided it, like this 1 became 0.5, but 0.5 is not an integer, so it would be rounded to a next integer, which is, for example, 1. And this 1 will become 2 because it will be multiplied. And here it was divided. So this way we avoid this 1, and we avoid the 3 the same way, and the 5 the same way, so we avoid all the numbers we don't need. So it's a simple trick, and let's implement it in Houdini. Though I showed only one axis, the method is applicable for all of them. So first we need to access the original point position by calling an attribute P. So if you go to spreadsheet, you can see all the attributes that geometry has. So this is points, vertices, primitive, and detail. So in points, you can see that we have a variable P, and it has 3 components because it's a vector. However, we need to access each component separately. And we can easily do it by typing, so let me make it big. So we need to type at P dot X. This way we're accessing the X component. And let's apply the knowledge we gained from that illustration. So what we have to do is take the same position and divide it by 2. Then we round it, rint, and then we multiply it back. And don't forget to add semicolon in the end. So let's repeat it for all the other axes. So y is the same, but divided by 3 because we have the model size 2 by 3 by 2. And the same for the last one. So yeah, hit apply, and there you have it. So let me show. Since we have much more points than we have the grid snapping points, well, let's fuse them because we don't need so many. Keep unused points. So yeah, and let me show you how the box looked. And the best part is that if our box is bigger, we also have representation not only of the surface but also the volume, so you have the points inside as well, which is great. However, since any random point can become a pivot for the next box, we have a slight problem. If a corner or an edge point is selected, our building wouldn't have enough space to have a proper connection. So let me illustrate that. So yeah, as you can see, if something like this happens, the building just looks very awkward. There is not enough space for a person from this room to enter this room. And even if it's in 2 points, it's still not enough. So that's why we need to tell Houdini that we do not need any corner or edge points. And we're going to do it with writing another vex node. So let me quickly go back to Photoshop again to show you how we're going to achieve that. And to avoid those cases, we're going to use a function called PCOpen. And what it does is that if we specify an origin, it will look for all the points inside of a specified radius, which is going to be 2, because that is the size of our modular grid, 2, in the x and z axis. And it will look for all the points out of the radius, so in this case, it will give us 5, because it also counts for the one that we specified as the origin. And if we repeat this process for everything, so let's see the outside one, the corner one will receive only 3 points, and this edge one will receive 4. So you can already kind of see the pattern here, and if we do it for all the points in the geometry, we can easily sort the points that we actually need. And you can see that all of them will have a 5, and all the outside ones will have a number smaller than 5. So that will be our constraint when we're going to sort the points. Let's bring the wrangle node again, delete wrangle, and name it delete edge points. Set it to points, and let's write code. So we should start with assigning a variable that will hold the point cloud. It should be an integer. I'll call it let be cloud. And write PC open. Then we need to specify at what input we're gonna look at. It's input number 1, but it starts the count with 0. We are looking for a position attribute, and the origin is the point position, so P. And the radius is 2.1. I just like to make it a little bit bigger. Just don't make it bigger than 3 or equal to 3, because then it will take the points from the bottom layer. So this one will start seeing also these points, and it will mess out with the count of the neighbors. And then we need to specify how many points will this point cloud hold, and it just doesn't matter 10. Next thing is we need to say that if the amount of points in the point cloud, so PC num found, so the amount of neighbors found, points, in the P cloud is smaller than 5, then this point is not valid, and we need to remove point from the first input, and we need to access an attribute called ptnum, which just states for the number of points. 1. And here you go. Let's check if it works for the other cases. So if it's 12, yep, 6, all works. So the next step is to bring everything into a for each loop. So let's condense the nodes into a subnet, so it will be easier to manage. And we will call it pcloud. And let's bring in the for each subnet. We will need the origin box, as well as we would need the bottom points of pcloud. And the reason for that is our loop is going to select a random point, which will generate in the following iterations new points. So it will basically create a branch. However, if we do not include in each iteration the bottom points of the original box, we can have only one branch, and that is not what we want. So you will see what I'm talking about when we start stacking the boxes. So let's bring in the blast, and we only want the points which y is smaller than 3, no spaces, and the delete node selected. So we will call it bottom points, and we will also connect it to the second input of the subnet. And as for the loop, let's name it into stack boxes, as well as let's rename the stamp name to stack boxes, and index stamp name as well, stack boxes. Yeah. It's just a good habit to rename those all the time, because if you want to layer for each subnets into each other and they have the same name, they will conflict. So let's copy point cloud subnet and dive into the node. So currently here we have only one box because we do not have any other previous iterations. And speaking of iterations, let's say that it's for each number, and currently let's have only one iteration. So, yeah. And also very important, Don't forget to uncheck merge results, because what it does is that every iteration is merged then into one big result. And that is not what we want. We want every next iteration to iterate over the previous one. So then we have to uncheck it. So make sure to uncheck it. So let's dive into it back and paste our point cloud. And since we don't have any other box yet, it seems like we can just connect this one here. However, what will happen is that once we have more boxes, for example, we will generate a new box and we will merge them. In the next iteration, we will have two boxes and they will run, both of them will go into the point cloud, which we don't want. So we need to limit that. We need to tell Houdini that we want only the last box. And that's where our box ID comes in. So let's call it locate. And we have to say that box ID has to be equal to the number of the current iteration. So we have to go up to the for each loop and for value stack boxes. That's how we name the stamp name, 0. And it should be primitive because our box ID attribute is for primitives, and delete non-selected. So in locate, yeah, still have it. Because we would say just delete, yeah, our box disappears. So delete not selected. And only this box will go to the point cloud. So here we have our points, and we need to also merge them with the bottom points, which are connected to the second input. So here, second one. So merge them together. So currently they're overlapping, which we don't want. Otherwise, this will have more probability to be the point that is selected. So we'll have to fuse them. Then keep on these points. And also we would need a height constraint. Otherwise our building might go very tall if every time in some cases it selects the top one. So I like to constrain it to only 2 floors. So let's call it height. And then we say that any point which y is bigger than 3 has to be deleted. So points. And no spaces. Okay. All correct. So here are points. However, we do not want to choose randomly. We want to make sure that the system knows which points are the ground floor and which are the top, and pick based on that. We want the bottom to have a weight control, so we can specify the probability of the building having more ground floors, as in most cases the bottom is always heavier than the top. So let's bring the wrangle node again. Let's call it pick random. It has to be over points, all correct. So let's write the code. So to indicate bottom and top floors, we would need 2 integer arrays, which we'll call top and bottom. We also need to set the wrangle to detail. Then it means it runs only once, because we will create a loop here that will run over the points, because we need to do it multiple times. So let's make a loop for the points. So to start with 0, it should be smaller than the total number of points. So in points from the input number 1. And with every step in the iteration, it will be 1 time bigger. So that's our loop. In this loop, we need to access position, because we're going to compare the position, and based on that, we will assign the point either to the top or the bottom array. So we need the vector position, which we're going to identify inside the loop. To grab any attribute, we need the point expression from the first input. We want to grab the p attribute, and we wanted to grab it from the point number of the iteration, so pt. Then we have to compare it. So if position y is 0, and I always like to round it, because sometimes Houdini makes this number very, very small, very close to 0, but not 0. Then it will make this expression false, which we don't want. So just in case, put a int there. And if that's true, we need to append it to the bottom array. And if it's false, then it goes to the top array. So apply, all correct, good. The next step is that we need to choose which array we're going to handle. And we also need to know what to do if one of the arrays is actually empty, because we cannot pick a random number from an empty array. So let's start with that. Let's say that if array top is empty, or array bottom is empty, then we technically do not need those arrays. We can choose a random number from the all the points that we have. So to do that, let's say that we need a random number, so integer random number. We're going to specify it here and not here, because we will also use it in the case that when this is not true. So random number would be equal to, and here we also would need a seed, so let's make that float. Let's call it seed. And if you just say channel and you write the name of the channel, which actually does not exist in this node, and then you press this button here, it will create automatically for you. And currently it complains because we haven't finished this line. So then random number would be equal to a random of the seed, and then just any number you want to add, 67. And we need to, usually random goes from 0 to 1. However, we wanted to go from 0 to the maximum point number that we have in our first input. So from 0 to a number of points in 1. However, number of points counts total amount of points. So if, for example, we have 7 points, the last point's number is going to be 6. So we have to subtract 1 and close. However, it can give us some floats, which we don't need. We want integers. So we say int. We're going to round it to an integer. And we're going to convert it into an integer, because even with int, it's still a float. So, right? Yeah, no errors. Good. So then let's handle the else case. So if both of those arrays are not empty, then we need to randomly select which array we're going to treat. And that's where the bottom weight comes in. So let's create a new channel, and we call it bottom weight. Right? So if both arrays are not empty, we need to say that random of seed. If that random of seed is smaller than our bottom weight, because if, for example, we have bottom weight of 1, random seed will almost always will be smaller. However, if we have bottom weight of 0, this will almost always be bigger. So that means that if our bottom weight is equal to 1, we want the bottom array to be treated. For this, we will need also 2 more integers, array length, and we will need array pos. You will see in a second why. So first we need to know what is the length of the array. So array length is length of the bottom. And then we need to randomly select not the point, but the position in the array. So it's basically absolutely the same as this one. I'm going to even copy it. However, we're not going to say that the last point is the maximum points number. We're going to say the last point is the total length of the array. And then the random number itself is the array, but a random component of that array. So array pos. Fine. All correct. And the same in the other case, however, with the top. So let's replace all the bottom with the top. So top and top. Apply. So once that is done, we need to run over the points again, and we need to compare the points number to the random number. And if they're not equal, then we just delete all the points. So in the end, we are left only with a randomly selected point. So for start with 0 again, smaller than the total amount of points, and bigger by 1. And then we compare it. So if the point is not equal to random number, then we don't need that point. So remove point from the first input and the point, apply. So yeah, we have only one point left, and let me illustrate you with a sphere or something. So yeah, that is a selected point, the only point that is left. And what will happen if we, let me press this, so we have the bottom weight again. If we make the bottom weight 1, it will go to the bottom, and no matter what kind of seed I choose, in most cases, it will always be on the bottom. The same as if I select 0, and if something in between, then it's like 50-50. So now, let's replace the sphere with a box. It's going to generate the next iteration points. So we can just go up and copy the origin box, bring it into the loop. So, but instead of having fixed numbers here, we're going to have a random one. But for that, we would need the random seed. So let's create let's create null, and we will call it seed. And I always like to color it so I can see it right away when I enter the loop. And we want to edit parameter interface, and we want to add a float, and we need to rename it. We need to say it's stack boxes seed, and the label is just seed. Right, accept. And what we want in the seed is the number of the current iteration. So every iteration would have a random seed. So I just can copy it from our locate node and paste it into the seed. Here you go. So that is the seed that is going to be used. So let's copy parameter and let's paste it into the origin box. And here we want to have the fit function again. This very similar to the one we already used. So we want to fit 0, 1. And we want to fit it between the numbers I found that work best for me were 2 and 4. So that is the possible sizes of our box. And we want to round it because we do not want unequal number. Apply. So, and then we want to copy that. Oh, I forgot one thing. It's not just the channel. We want to the random of the channel. Right. So let's copy that. And let's put it in Z as well. Just make sure to add some number, like, I don't know, 54, so that the random function is driven by a different number, because it will have different values. Because if you have two random functions and both of them have the same value, they will give you the same result. Apply. So yeah, that is our box. So we want to copy it, and the box ID has to be the same number as the iteration, but one step bigger. Let's copy it. And we want to merge it with our all the other previous iterations. There you go. So let's go up and let's add more, and you can see it works. Add more, yep. It keeps adding the boxes, and let's also make a global control. Let's call it out, and do the same thing. Just add a float. Let's have it global seed, and as a label just seed. And we copy it and we bring it into the seed here. So just paste relative reference, just do the lazy way, then cut it out and paste it here. So the seed now is affected by both the number of iteration and the global seed. That is why I like to put it into a separate null node, because then it's easier to control, and then this fits to all the other parts. And we also, the seed, also we have to include it in our pick random function, I mean node. So yeah, all good here as well. And our out seed, and you can see it gives us different results. And let me explain you why we added the bottom points by entering the loop. So it will show us the latest iteration. And merge. So you see, so this is the last box we added. There's a point cloud, only 2 points. However, we also have options to add the box on bottom, not only to continue the previous box. So that is the end of the first part of the first chapter, and I'll see you in the next one. Hello and welcome back to the part number 2 of the first chapter. So we left off with having stacked boxes. However, as you might have probably noticed, they do not account for self-intersection. So in this part, we will convert the boxes into one body mesh, as well as we will break the modularity a bit, and we will assign our first attribute that will be fed to the roof and the support systems. First, let's compress the nodes into a subnet, which we will call stacked boxes. So select everything except for the out, and click here, and call it stacked boxes. To eliminate self-intersection, we are going to convert our boxes into VDB, which basically represents our mesh in voxels. So let's bring VDB from polygons. And we want our voxel size to be half of the default one, so 0.05. And if you don't know what voxel is a representation of a value on a 3-dimensional grid. You can think of it as a 3D pixel, and your voxel size is your resolution. And the most important part is that voxels also represent volume, so they're not like polygons, which only give you the surface. However, we do not want voxels, we only want them to eliminate all the interior intersections, after which we want to convert it back to polygons. So now we need to convert VDB, and we want polygons. Okay. So you can see we get very dense mesh. However, it eliminated all the interior intersections. So that is exactly what we want. So let's bring transform node just to make sure that it rests on the bottom. So it's easily done by saying $y minimum. And the next step is we want to do absolutely the same algorithm as we did when we wanted to constrain our point cloud to the grid. So we just need to bring, this next node that we already wrote in the previous part. Just copy that and bring it here. However, if you enable point number, you see that we have a lot of points, which we don't need, so we just need to fuse it again. And here we go. That is our base. So the next step is to break the modularity a bit, but first let's compress the nodes into another subnet. So select all of them, and we will call it VDB base. So what I mean by breaking the modularity is that whenever we have a sticking out piece like this, it will be converted into a half block to be supported by small arches, like on this image here. So as you can see, it's not full size, and it will be supported by pre-made set dressing modules. So if you use the same seed numbers as I did, you should have the same, and if your input is 2.48, otherwise, just find a similar case in your pool where you have a block like this. So how are we going to detect whether a block is sticking out? Let me illustrate you the algorithm before we write it. Let's imagine it is our building's floor plan for all the floors combined, and the squares represent faces from 1 to 11, and these faces are held by points. The way we're going to determine that the block is sticking out is by looking at the amount of direct neighbors, and by direct, I mean that they have to have two points in their connection. And if the face has only one direct neighbor, that means it's sticking out. So we're going to look at each face. So let's imagine we're currently checking face number 4. And we're going to access its points. And by accessing its points, we're going to look at how many faces the point holds. And we're going to do it for every point. So this point holds faces number 1, 2, and 3. And we're not going to count the face we're actually accessing. So this point will hold 2 and 5. This one is 8, 9, 5, and 3, 7, 8. And then we will collect all this data in one array. So 1, 2, 3, 2, 5, 8, 9, 5, 3, 7, 8. And then we're going to look at numbers that we see twice. So 2, 5, because we want only the direct neighbors, which means that they have connection in 2 points. And then we're going to count how many of these direct neighbors we have. So in this case, it's 4. And we need only the face that has only one neighbor. And this is the way we're going to find which box is sticking out. So the first step is to convert our building into a floor plan as illustrated earlier. Unfortunately, if we just take a transform node and we collapse the whole building and then we fuse it, we will get overlapping faces. So like here, there are multiple faces on the same position, which will mess with our algorithm. So to avoid that, we would have to separate top and ground floors by bringing in blast. If you have more floors, you might want to write a loop for that. So this will be our ground floor. So we'll do it by position. So more than 3. And we want to keep points, delete non-selected. And the same we want to do for the top floor. Top floor. The position is bigger than 3. But basically what we want to achieve is to delete all the overlaps from the top floor, which we are going to do with vex. So let's bring the wrangle node. Wrangle. This will be for the top floor. And we will need to connect the ground floor to the second input, which I will explain in a second. We have to set it to run over primitives. And there is a very handy expression called intersect, which takes a point and a direction and checks whether an intersection occurs with a specified geometry. That is why we plugged the ground floor to the second input, because we can specify it by input. However, we are currently running over primitives. And so how do we select a point? We will take primPoints expression, which gives you an array of all the points that belong to the primitive. So we will need to create an array. I always like to name it PTS. And it is primPoints. Then we need to say from which input we're going to take the primitive. Comes from first input. And the primitive number is the current one that we are running over. And no caps letters. But we do not want the points themselves, we want the primitive center. And we can easily calculate it by adding all the positions of the corner points and dividing them by 4. So let's implement that. We would need a for each loop, where we need to set the variable pt and tell it the array from where the variable will be determined. That is why it's for each and not for. And from each of the points from the primitive, we need to extract the position. So let's create a variable pos. And we will identify it here. So let's grab the position. So point from input number 1. We need the position attribute, and it is from the point. And it's not just equal, because we need to add it. But it's not going to add it if our variable is not identified. So we have to start somewhere. So let's start from 0. And we just add. If you type plus and equal, that means it will add to the previous value. So after that is done, we can find the center, which is position divided by 4. Let's actually bring it bigger. So we have more space to write. So for the intersection, we would need 2 vectors, vector PW and UVW. Those vectors are needed for the expression to work, and this is just vectors where we're going to store the intersection position, and this one it will store the UV coordinates of the face where the intersection occurred. And now let's write the intersection expression. Let's call it intersection, and it's intersect. It needs to know the input number, so it's 0. It needs to know the point position, which is center. It needs the direction. Our direction is just straight down, so 0, minus 10. Be aware that if you just write -1, the ray from the point will only go as far as 1. So if we have a floor that's actually the distance between them is 3, it will tell you that there is no intersection, even though there is one. So make sure to specify a number big enough. So 0, and then we just add PW and UVW. So, yeah, all correct. So now we need to check whether intersection happened. And in the intersection expression returns you the number of the primitive. However, if it returns you -1, that means that there is no intersection. So we need to check that if no intersection is false, then we remove the primitive. So we write remove prim. Need to specify the input number of the primitive, and here you have to say 1 or 0. It's a boolean. It asks you whether you want to keep the points, to delete the points, and yes, we want to delete the points. Make sure that in intersect function you specify the input number 1, because we want to check the intersection with the ground floor, not with the top floor. So 1, yeah. So here we have the faces that do not intersect with the ground floor. So now, if we merge ground floor and the top floor together, and we collapse them as we did earlier in the very beginning, by saying that the scale y is 0. So now we can just fuse them, and we're not going to have any overlapping faces. So the next step is to identify the sticking out block. But first, let's rename the wrangle node to delete overlap. And let's compress these nodes into a subnet that we will call building footprint. And now let's bring a wrangle node that will identify the sticking out block. So we will run over primitives. Let's bring it bigger, since it's going to be a bit of code that we will have to write. So we will need to access points again. So let's bring in points and an array for it called PTS. So print points from the 0 input current number of the primitive. We would need 2 arrays as well, one to hold the data from the point we are accessing, and the other one to hold the sum of all the data. So let's create int nays, short for neighbors, pcheck, and nays pcheck all. So next we will need to record all the points from the primitives with the for each loop like we did earlier. We will need to access the PTS array with our points from the primitive. And what we will do now is that we will access the primitives that this point holds. So we will identify our nays pcheck, which will be equal to point prims. So this is an expression that will grab all the primitives that this point holds, and we need it from input number 0 and pt. And then you just need to append this data to our nays pcheck all, and we need to append the current array. So apply, no errors, good. And now we will need to find all the direct neighbors, and for that we will have to run over all the primitives. However, to make the job a little bit easier and faster, we won't run over all the primitives, but we will run over the primitives until the maximum number of the primitives in the array. So we will need to know which is the maximum primitive number in the array, which is easily done with a max function. So let's call it max number, max nm, and we just say max from our nays pcheck all. So now we know which number is the biggest one, and our loop will go from 0. So first number is 0, and it should be less or equal, because we also need to run over the maximum number, and with every step it will be bigger by 1. Since we're also going to count how many times a primitive is in the array, we will need to create an integer that will count for us, so we will call it found. And we will also need an array that will hold all the direct primitives. So let's create the array. So now, in the loop, we need to check all the primitives. However, we do not need to check the one we are already running over. So let's write a condition. So the number which we're checking should not be equal to the number that we are running over currently. So should not be equal to primnum. If that is true, we can run our loop. Since every primitive we're going to run over, we're going to count from 0 for that primitive. We need to identify that found is equal 0. Otherwise, for example, if we found it 3 times in the array and we haven't specified that it's 0 in the next iteration will start counting from 3, which we don't want. We always want it to start from 0. So now we need to access our loop. So again, for each. And we will need to access our check all. And we just need to see whether the current value we're checking in the array equals to the number of the primitives that we're checking. So, and if that's true, we just say that found is bigger by 1. So after we check all of that, we need to check how many times we found our number of the primitive in the array pcheck all. So we say if found is bigger than 0, so we found something, and the found should be divisible by 2, should be equal 0, then this primitive we're checking, nm, is a direct neighbor to our primnum. So then we append it to the list we created earlier, which was called nays prims, and we append the number 1. And we have an error somewhere, reference to our identifier variable n. Oh yeah, found it here in 4. I forgot to write nm, I wrote just n, so apply. Yeah, all correct. So the next step is to say that if length of the array that holds all the neighbors is bigger than 1, then we do not need this primitive. So remove prim, 0, primnum, and delete the points. Because as I illustrated earlier in Photoshop, we only need the primitives that have only one direct neighbor. So if the primitive has more, it is invalid, we don't need it. So apply. Some other mistakes, candidates, nays prims, as should be here as well. Apply. Accept. And as you can see, only the one that we are looking for is left because it has only one direct neighbor. However, that is not all. There's one more step we need to do. Let me bring you the pictures so you understand what I'm talking about. So as you can see here, we will have these modules, but to place them correctly, we need to know the direction from the block to the body, which will drive the orientation of the supporting modules. And for that, we will need to write a bit more code. What we're going to do basically is going to take the center of the primitive that is sticking out block and the center of its neighbor, and we will create a direction vector that we will write to an attribute. And this direction vector will drive the orientation of the modules later on in the system. So for that, we need to say here in the if statement, so if we do not remove it, so else. So in the case where this is actually equals to 1 or smaller than 1, but it's not going to be smaller than 1, because in all of our cases, it will always be one solid body. So in this case, we need to grab the center of the primitive, of the current primitive and its neighbor. And for that, we will have to write a custom expression. So let's go in the beginning of the code. So in Vex, we can write our own custom expressions that we can call later in the code. For this, you just need to say what's the type of the expression you have. What is the value that it's going to return? It's going to return as a vector. We will call this expression get prim center, and the input going to be the prim number. And here we will just repeat what we did earlier when we were detecting a center of the primitive. We will grab the points. So let's call it points, and we will call for prim points from 0 input, and we need to access this variable as a variable to identify once we write the expression. So we will need our position, which first will equal to 0, and then we will go into a for each loop. We will say that for every point in points array, we want to add to the position of that point. Point, 0, p attribute, and from point. And then we will have vector center, which is position divided by 4. And then we return the center. So this function will get the primitive number, and it will return us a vector of its center. So, oh yeah, I wrote plus here. Sorry, it should be equal. Yes, all good. So now we can call to this function, which we're going to do. So vector, we will call it center1, C1. That we say get prim center, and we will say which number. We need the current number of the primitive we are running over in the wrangle node. And then we need to get the primitive center of its neighbor. Since we know it's going to have only one neighbor, what we do is we go to our nice prims, and we ask for the first value. So that has an index of 0. And the vector direction will be a normalized version of the subtraction of these two vectors. We're going to use this a lot. We will often find direction vector between 2 points position. So just remember that if you subtract 2 point position, you will get a vector direction of which goes from C1 to C2. So once we have this vector direction, we need to write it to the points. So we'll have to go into another for each loop, and we will access the PTS array that we created in the very beginning of all the points that this primitive holds. And we will just write to them the value of the attribute. So set point attribute. However, we cannot write to an attribute that does not exist. So for now, we will write it to a normal. And we'll write it to the point P. We'll write the value direction, and we will say it to set. There are other modes like add or subtract. Set just sets this number, no matter what number was before, it will set it to direction. So apply. And if you click now on the display normals, should give us, I think it just doesn't have a normal as well, so we'll have to click on facet and say pre-compute normals. Yeah, and as you can see, let me turn this off. All the normals are pointing to the body. So when we will have these supports, they will have a correct orientation towards the body. So let's name the wrangle node. But since sticking out box is too long, let's label it as closed balcony. So find closed balcony. So in this case, we only have one primitive. However, there can be more. So we will need a for each loop. Since this loop will modify not the primitives of the balcony, but the primitives of the body, let's plug the body in the first input and the primitives of the balcony into the second input. So we want to run as many times as there are balcony primitives. So let's say it's from 0, and we want to run it as many times as there are primitives and prims in the second input. So op input path of this node of the second input. And since it will give us a number of all the primitives, rather than the last primitive number, we need to subtract 1. So now it will run only once, because we have only one primitive here. But if you would say have a more, so let's have it's a box where we have 6 primitives. So you plug it here, you see it's 5. So you can see, yeah, 6 primitives in this node. Let's name this loop treat body and enter it. So the first thing we'll have to do is to locate the balcony primitive. So let's grab the second input, and we will need to locate the primitive, the number of which is equal to the iteration number. We already did this earlier, so we're just going to repeat the same process. So we will need to delete the same thing as stamp, and it's for value 0, and don't forget to put it in the bracket. Yep. Delete primitives and delete non-selected. So there it is. We call it locate. We don't need the whole primitive. We will only need the points that are close to the body, because we will treat the body with a group node. So let's first sort the points, so sort, and we're going to sort them based on the normal that we created earlier. So point, sort along vector, and this is a vector of point, and it's from the input number 1, so the same input path, 0, and it's from the first point. We want to grab the normal and x-axis. Copy that. So this is the y-axis, and this is the axis, so the second one. So as you can see, our points sorted according to the vector we have. Let's just reverse it. Yes. And now just locate the points we need. Let's call it locate points. Locate points. And we only need 0 and 1. Delete non-selected, that's points. So as for the body, we will group based on these points here. So let's call it group based on bulk points. So in the bounding, we will group by bounding box. I'm going to say enable, and the center of this is going to be the center of the nodes that we just created. That is called locate points. So locate points. We need to grab the x-axis, so d/x, and same here. C. However, we do not want the y, because we always know this is going to be on the second floor. So we know the center. The center is 4.5. And I just realized that we do not need the reverse in the sort one. So yeah, sorry about that. So now we just need to specify the correct size. So since we already know the size of our module, and it's the same in z and x axis, we can just say 2.1. However, if you have different sizes, you can determine the difference, like which one is the widest one, by looking at this node and seeing that this is the widest in z-axis. So that means that the orientation of your module is also in the width of it lies in z-axis. So you can determine the width like that. But since we have the same module size, it does not matter. And the height is 3.1. So once we have this, we need to make sure that we transform it. So let's bring transform node. And here we're going to transform based on the normals of the locate, because we wanted to transform it closer to the body. We will be transforming either in z or x, so that's how we're going to do it. So we're going to say point locate 0 normal and 0 in x. But we only want to transform the group 1. So as you can see, just smash it into the body completely. And let's actually rename the group. So let's call it bulk points. I just need to rename it here as well. So bulk points. So we don't want 2, we want just 1, so leave it like this. And I want to do the same in z-axis, just in case there is a different orientation. Like now it's not going to do anything, because the normal of the locate here is 0 in z. But imagine that this primitive body is actually here, and it's going to push it here. That's when it will transform it here in z. However, there's also one case. Sometimes there is a sticking out piece, but it's on the foundation rather than on the first or second floor. So in that case, it will transform us only 2 points, which we don't want. We only want to transform a full primitive when it contains 4 points. That will be our condition. So let's bring switch. And we're going to say that if endpoints group, so if in the group of the node that is called group based on balcony points, if the group called balcony points is bigger than 2, only then we want to and we currently grouping primitive, which we don't want. We want the points. So here we have 4 points in the balcony group. So this expression is true because 4 is bigger than 2, and we just need to switch the inputs. So in this case, only in this case, when the number of points is bigger than 2, this will happen. The transformation of our balcony will happen. So let's group all the nodes that we created into a subnet. We will call it closed balcony, closed balcony. Next step is to create all the attributes that we will need later in the system, such as supports that can be both full or partial, and roof, floors, and walls. To identify those, we will need, first of all, normals. So let's bring facet node. We say post compute normals, and we need unique points for each primitive. So that's what we want. We will also need area attribute, so let's bring measure node. And we want the area type, and we don't need override name, because that's all good. And to write the attributes themselves, we will need a wrangle node, so attribute wrangle. And let's call it initialize. We will run over primitives. So the first thing we will need to do is to grab the points of the primitives, so PTS array again, and we will need prim points from the first input from the current number of the primitive we are running over. And we will need a vector. Since all the points have the same vector of the same primitive, we will need only vector of the first point. So from the first input point, we will need normal attribute, and from the array, and we will need only the first one. And based on that, if this normal is bigger than 0 in Y, that means it's a roof, because as you can see, if the normal points up, it only points up in one case, when this surface is a roof. So we'll create a type. It's a string type, so don't forget to say it's S. So S type equals to roof. Else if the normal.y is smaller than 0, in this case we can have multiple cases, because not only it is the floors that point down, but sometimes it is the supports as well. So we need to identify whether those are the supports. So in this case, we will need a new vector position, and we will grab it absolutely the same way, only from the first point. So because we only need the position in Y, and all the position in Y, if it is as a floor or support, they always have the same Y. So we can just grab the first point. So we need the P attribute from the first index of array. And if the position in Y is 0, that means it's a floor. So S type equals floor. Let's bring it bigger so we have more space to write. That is a floor. Else, in our case, that means it is not a floor. That means it's a support. So let's write S type means support. But what type of support? Partial or full? And that's why we had this measure node, which measured our area. So we just need to grab that attribute of area, because it already exists, And if the area is smaller than 4, because our one tile, 2 by 2, its area is 4. So if it is smaller than 4, that means it is a support of the closed balcony that we created earlier. So what we need to do is we need to grab the type attribute again, and we need to add to it that it's a partial one. Partial. In another case, we will add that it is a full one. And in any other case, it is a wall. Done. Apply, initialize. So let's hide this. And to make sure that we created everything correctly, let's create a marker. So D. So it's in visualizers. We will add a new one, seal visualizer, a marker. And we will call it type, label, type. We will need the attribute of type, and it will be a text. And let's make it some more visible color. Font size, large, close. And as you can see, all works correctly. So these are all walls. That's correct. Support full, support partial. Oh, no, support full. We're missing an slash here, line, and all these are floors. So let's grab all of our nodes here and create a new subnet, and we will call initialize attributes, and we will grab everything that we created, all the nodes, collapse it into another subnet, and we will call it create body base, in this capital. So this is the end of the part 2 of chapter 1. We created our base that is ready to be treated. In the next parts, we're going to create the roof, and it will be driven by the attributes and the surface that we created in these parts. Hello and welcome to the part 3 of chapter 1, where we're going to start with the roof system. First thing we have to do is to isolate the roof surface, which is easily done with the attributes we created earlier. So let's grab blast node and specify that we want only the type roof to be present. So delete non-selected of the primitives type roof. Let's call it locate roof. Let's compress it into the subnet right away, and we will call it roof base. So as you can see, we just have square tiles. How do we first of all make sure that the roofs occupy different space on those tiles but do not exceed them? We will write a vex node that merges random tiles into one, thus leaving us with a random pattern. Let me illustrate you the algorithm. Let's imagine that this is the view of our roofs from the top. We will check a random face and see if it has a direct neighbor, which is, as you probably remember from the previous parts, we agreed to be a primitive sharing 2 points. We will randomly pick a neighbor out of all the possible ones, and we will merge them together into one primitive. Important to note that the new primitive will also have only 4 points, which means for us that not all the close primitives will be direct neighbors anymore. So if you look at this primitive, it will have 4 points. However, it will share only 1, which makes it a non-direct neighbor. And the same with this one, and this one, and this. We will repeat this algorithm until there are no direct neighbors in the shape at all. So in the end, we will have something like this. So let's implement it in Houdini. So to be able to track direct neighbors, we would need to fuse the points. So let's bring the fuse node, connect it, and let's compress it into a subnet right away, and we will call it merge roof shapes. So let's jump into it. We would also need to randomly sort primitives we already have, so let's bring sort node, and we need to put it on primitive and random. And let's also hide our markers. So press D and uncheck the type marker we created. Visualizer, sorry, not a marker. So the next step is we will need a for each loop. Let's call it merge shapes. And uncheck merge results and each number, and for now let's make it run only one time. So let's jump into it. So here is our each. Before we start writing the code, we would need attribute. So attribute create. So let's call it attribute keep. So it's a primitive attribute named keep. And the reason we need it is to indicate which primitives are going to be merged in this loop iteration. And we need it inside the loop, so every time the loop starts, they are all zeroed out, because we do not need to keep the information for the next loops. So now we can bring our wrangle node to be wrangle. Let's call it find neighbors. Let's color it so we can see it right away and bring it bigger. Run over details, so we will need it only once. And the first step will be to find which primitives have neighbors. So we will need to create an array to hold the points. And we will also need to an integer variable to hold the amount of found primitives that have neighbors. So in the beginning should be 0. And we will need a loop to run over all of our primitives. So let's call per num, and it should be smaller than the amount of primitives in our first input. And with every iteration, it will be bigger by 1. Inside of the loop, we will also need multiple variables. So let's create them. We will need a neighbor count. We will also need a neighbors check array, as well as the neighbors array. So in the beginning of the loop, we need to make sure that all of those are zeroed out. So the integer equals to 0, and all the arrays are empty. So then we need to grab the points. So the points array is prim points of the first input and primitive number. Now we need to record all the points from this primitive, so for each. In the PTS array. And now we need to identify the neighbors check. So point prims from the first input and the point of our loop. And we will need to append this to all the neighbors list. So once we have all the neighbors in a one big list, we need to find neighbor primitives. For that, we will also need multiple variables. So we will need a max number, because we're doing the same as we did in previous parts, where we cap it at a maximum number of the array. We would also need the found to count how many times we found certain number of the primitive. And we will need a new array, neighboring primitives. So here we need to identify those. So maximum number will be a maximum of our neighbors array. Found should be equal to 0. And the neighboring primitives should be empty. So now we will need a new loop that goes from 0 till the maximum number. So it should be also equal to the maximum number. and with every step it should be bigger by 1. So here we also need to zero out our found, and we will need to access all of our neighbors. So n in neighbors, and if our n equals to the number that we are checking in the for loop, then our found is true and we add 1. So after that is done, inside of for loop, so we're still checking the primitives, we need to say that if found is bigger than 0 and found is divisible by 2, that means that this primitive is a direct neighbor to the primitive that we are checking. So append to the neighboring primitives and the primitive. So yeah, the next step, that if the length of our neighboring primitive list is bigger than 0, then it is a primitive that we should keep. It's the primitive that we're gonna look at because it has direct neighbors. So let's set the attribute to the primitive. In the first input, attribute is named keep. We need it to the current one we're checking, and it should be equal to 1 and set. Oops. We also need to set the same primitive attribute to the one that is the neighbor of our primitive. We just need a random one, so let's just say the first one will always be the one that is going to be kept. So the same one, set. So we found the primitive, so found primitive. And now, what is very important, we need to break this loop. So if that is true, this loop stops. So as soon as it finds this condition, it will break the loop. We do not need to run it all for all the primitives. We only need to find one that satisfies to this condition. Yep. So another step that we will need to do is, if you go outside of our loop, our for each loop, the subnet, you will see that there is a stop condition. So we will write one thing just for the stop condition to work. So if the found primitive is equals to 0, we will write a detail attribute. So integer, and the name of the attribute will be stop equals to 1. Otherwise it will be equals to 0. What it means is that there are no primitives that were found that have direct neighbors. Then the stop will be equal to 1, which means that we will stop our subnet. So apply. There are some errors. Well, let's check it. Okay, one error is here, so apply. Another one is here. A nice check here. Apply. Okay, all accept, all good. So let's see which ones he decided to keep. So my assumption, this should be 1, because this one doesn't have any 0, 1 doesn't have any direct neighbors. So the 1 should take one of their neighbors. So let's take last node. Let's call it keep, and we say if keep equals to 1, then we would delete non-select. Something is wrong. We forgot to make an exception in our loop where we are checking for all the primitives and looking whether any of those equal to the neighbors found. Here, we need to specify that nm should not be equal to prim num we're checking. So include this one as well. Just press tab, apply. So now it should act, yes, it acts the way we expect it to act. So after we have these keep primitives, let's isolate the ones we do not want to keep. So no keep. So the keep is equals to 1, and we delete those. So primitive, yes. And the keep ones, we want to merge them, and we want to merge them the way so that these points no longer exist. So for this, we need the divide node. And we need to say that, first of all, uncheck convex polygons and check remove shared edges. So it will remove the edge. However, the points are still there, and that's why we will need facet. And we will say that remove inline points. So here you go. And we will just need to merge it back with our no keep primitives, and we need to fuse them back for the next loop. Otherwise, we have a unique points on these locations. So we fuse this. That's all good. So let's check if it works. And as you can see, it works perfectly. We have a random pattern, and the best part is that if you change the seed, your pattern also changes. How cool is that? So, however, let's go back to our stop condition, because here we can specify anything. You can specify 100, but the thing is to actually run 100 times, so that's not what we want. What we want is that we need to specify in the stop condition that there is a detail in find neighbors, yes, so correct, which is called stop of index 1, because it's not an array, so just needs the first index. And if it equals to 1, it will stop. So now we have a condition, yes, and at a certain moment it is true. So here we are, having our random pattern generation that is ready to be converted into the roofs. The next step would be to make the roofs. But first we need to understand what we are trying to achieve. If you look at the real life examples, you can often see that the roofs merge into each other, like here. Sometimes they do it though they're on different height levels. Like in this example, this big roof merges into the one on the higher level. These are the images of Scandinavian wooden churches, and that's where the idea of stepped roofs came to me. So let's imagine we have two primitives and they are to be converted into the roofs. We want to make sure that the appropriate roof is merged with its neighbor, and the neighbor is on a bigger height level, whether with the means of a platform or just by having a different roof angle, like this. We want to avoid having roofs like here, unless there is another roof on this side that this one merges into. It is a big task, and we will approach it step by step, and we will start with determining the roof directions. Let me show you the algorithm that will help us to achieve that. So here's our roof illustration from the top view. Let me show it to you in more schematic view. We will be checking each primitive and looking for other primitives, the border of which it touches with its 2 points. So let me show you. We will resample every single primitive except for the one we're checking, and we will see whether the points of the checked primitive sharing similar positions with the resample points. So what it means is that these two are sharing similar positions. This means that this orange one is a touching primitive of the checked one. This way we will determine the direction of the checked primitive, and we will do it for each primitive that we have. So first of all, we would need to resample our roofs. So let's grab resample node. And let's enable the points so we can see. I think 0.2 should be enough. And we will also need to create a roof ID so we can access the resampled version inside of for each loop. So let's bring attribute create. Let's name it roof ID. So roof ID, class primitive integer, type integer. And the value is $PR, which means the same value as the number of the primitive. So if you go to the spreadsheet and you click on the primitive, you see that the roof ID is the same as the number. So let's bring for each subnet, and we will need the non-resampled version as well as the resampled version. Let's call it roof direction. It's each number. Let's rename the stamp name as well. So roof direction. and here as well, roof direction. And number range for now, let's make it go only once. And we do need merge results, as we're going to treat each primitive separately from the results of the previous iterations. So let's go inside. We will need to select a roof, so let's bring up blast node. We will call it selected. And group type primitive. We will need to delete non-selected, and we want to select the same one as the number of the iteration. So stamp for value roof direction 0. So here is the first one that is selected. And we will also need to grab all the other ones, but of the selected version. So let's copy the blast and connect it to our resampled one. And we will call it non-selected. And just uncheck delete non-selected. So here we have all the other roofs, except for the one that we have selected. So in this case, I see that we have this one as the first one, and it's not going to have any neighbors for us to check. So let's go up. And we will grab a sort node and just offset the number of the primitives. So this one is the first one, just so it is easier for you to see what is going on when we're going to write the code. So primitive, just shift it and shift it by 7. Okay, we will delete that node later. So let's go back inside. And our selected is 0, 1, and a non-selected one is 3. So actually this one is also not going to have any neighbors, so we will need this one to be 0. So yeah, 13. Awesome. Let's go inside. So yeah, that is the selected one, non-selected one. The next step is to bring the wrangle node. So attribute wrangle. We'll connect it to non-selected. We will also need the selected one connected to the second input. Let's call it find touching, and we will color it. So it should run over the detail only once. Let's bring it bigger. So let's start by accessing the points of the selected primitive. So integer of PTS, square brackets, prim points of the first input, very important because we connected it to the second, so counting from 0 it is 1, and it is only primitive, so index 0. We will also need an integer to hold the point cloud, which we're going to use to look for the points of similar position. So int pcloud, and those positions we also need to store, so let's create a vector called position, as well as we will need 2 arrays, nace pcheck, where we're going to store the data of the point, as well as we will need nace all to store all the data from those points. When we're going to run through the point cloud, we will also need to extract the point position, so we will need another integer, which we will call ptnum. So let's create our for each loop, and we're going to access the PTS array. Then we will identify the position. So we will identify the position of the point that is in their array. So point, very important, of the first input, because we are accessing the selected primitive. So we need the P attribute and the point P. Then we will identify the pcloud with PCOpen function from the 0 input, because we're going to look at the non-selected resampled primitives. So grab the P attribute. We will look from the position of our point of the selected primitive with a very small radius. And the maximum number of points we want is actually only 1, but you can find any number. Let's put 2. And then if something was found for PCNum found of the pcloud is bigger than 0, so something was found, we will access the array with PCIterate function. PCIterate of our pcloud. And that is why we had this PC PTNum integer, because now we will bring the point number from the point cloud array. So PC import from pcloud. We want to grab point number, and we want to import it into the PC PTNum integers that we created. So now that we know the point number, we can identify our neighbor's pcheck, and we will grab the primitive that belongs to this point from the 0 input and from the number of point that we just imported from the point cloud. And this array we will append to the nace all that stores all the data. So let's append that. So p check. So apply, no mistakes, good. So now we do absolutely the same algorithm that we already did a couple of times. We will create a max number, which is the maximum number in the array that we have, so nace all. We will need a found, and we will need a final array that will hold only the primitive numbers. So now we will create a loop for all the primitives. And with each step it's bigger by 1. So for every number, the found will be equal to 0, and we will check our array that holds all the data, whether it has the number we are looking for. So if n equals to nm, then our found is bigger by 1. So after that is done, we check whether found is bigger than 0 and whether it's divisible by 2. And that if that is true, this number belongs to our final array. Apply. So no errors, great. So if we did find some neighbors, some touching prims, then we need to identify which one is the one we are looking for. So for loop, we will run for all the primitives of the resampled version. First, we need to access the array. So in the array, so our final array with all the prims. And if pr equals to the neighbor, then it is the one that we should keep. However, how do we identify that? For that, we will need a new integer, which we'll call found n, the neighbors. And for every primitive, it will start from 0. And if we did find it in the list, we will say that it was found. And only if it was not found at all, we will remove that primitive. So remove prim. And from the first input, we will remove the pr, and yes, we'll delete the points. And if none of the primitives was found, like no their neighbors, then we just need to delete everything. So else, copy the loop, and we just remove everything. Remove prim 0 pr 1. Apply. So fine. Okay, we do have an error. Oh, in 16 it's not a point, it's point prims. Apply. And as you can see, we correctly identified the touching neighbor of our selected primitive. However, sometimes there might be more than one, so we need to make sure that in the end it is always only one primitive that is found. So primitive, delete non-selected, we only want to keep the first one. Then how do we determine the direction? Because if we just use the centroids of those two primitives, we won't have a correct vector. Because sometimes the shape might be much longer, and then it will offset the centroid, and the vector, if we round it, it will point in the wrong direction. So what we need to do is we need to divide it. And first of all, we need to get rid of all the points we don't need. So remove inline points. And we want to divide it according to our modular grid. So uncheck convex polygons, check breaker polygons, and the size is 2 by 2, and here it doesn't matter 100. So now we want to keep only the touching primitive. So we will need to write a new wrangle. We'll connect this here, and we'll copy the divide, we'll apply it to the selected one as well. And we'll call it keep touching prims. So we will run it over the primitives. Let's make it bigger. So what we will do is we will run over the points of the primitives of the first input, so the previously resampled one. We will need to grab position, as well as we will need a found integer, which will be equal to 0. We will access the points, so int p in PTS, and we will identify the position. So grab the p attribute. We will need a point cloud again, so let's create an integer for that, point cloud. So point cloud is PC open, but this time we will look at the selected divided primitives. We will look at their position from the identified earlier center with a smaller radius, and doesn't matter 4. And if we see that it did find something, so PCNum found of the P cloud is bigger than 0, we say that found is bigger by 1. And if it found less than 2 points, we do not need that primitive, so remove primitive from the first input, primnum, and remove the points. Apply. And as you can see, we'll be left only with the correct piece, from which we can easily find the directional vector. So to visualize our direction of the roof, let's bring in clip node. And we will set that the origin is a centroid of current primitive. So let's grab it from the previous input, and we will say that we want the x, and we want the z, and y. And the direction will be determined by the subtraction of their centroids. Let's copy this. However, the clip node is a bit weird. You kind of need to invert z and x. I find it a bit counterintuitive, but that's the way it works. So, and this one centroid we will grab from keep touching prims. All correct. We will copy all the expression, and we will make the same one in z with x axis. And y we don't need, and we say keep all the primitives. So the direction is correct. Yes, that is correct. So now it is time to assign the attributes. So let's bring wrangle node again, and we will say init attributes. So we need to make it run over the primitives, because we will assign the attributes to the primitives. And we will need to connect the find touching to the second input. And if we did find some touching primitives, we will write an attribute. However, we will write an array attribute, because you want to record all the touching primitives, and sometimes there are more than one. So before we do that, let's create that attribute. So I array at, and we will call it touches, and we will create it empty for now. We will also create an array int touches, and let's start with a for loop. So we will need to run over all the primitives that are in the primitive, that are in the find touching. So for that we will need an integer to hold the ID. ID is equal to prim of the first input, and we will grab the roof ID that we created earlier, and we will append it to the list. We'll append it to the touches, and we'll append the ID. And then we say that the attribute we just created equals to touches. So if you go to spreadsheet, you see that in our array we have only one. Touches only one. However, if there are no found touching primitives, we can just skip these two steps. So say that if primitives in find touching is equals to 0, so in this case it's not true, and it takes this branch. And in the end we just need to create a roof ID as well. So attribute create, call it roof ID. So the class primitive type integer, and we just need the stamp. We need to have the same ID number as the number of the current iteration. So value based. Awesome. So let's check if it works. Let's say that we need to run it over all the primitives that we connected. And it works as expected because we haven't specified what to do if there is no touching primitive. However, if we check other cases, by accident I put the out in the closed balcony, so make sure to extract it. So let's extract our out. So say Ctrl X. We need to bring it all the way up on Ctrl V. We need to copy parameter again, and we need to reassign it, unfortunately. So let's remember where it was. So in stacked boxes, it's the seed value, and we need to bring it. So paste relative reference, copy that, replace it here, apply. So nowhere else, I presume. That's all we had to do. That is why it's very convenient when you have only one node that contains the seed for the loops, because then you don't have to reassign it everywhere. That is our out. Let's color it so we don't forget not to touch it again. And these two, we'll color them light blue. So let's check our out, and with other cases to check whether our direction works the way we expect it to work. And yes, this merges here, that's correct. This one's merged here, correct. All correct. Yes, and let's check whether the touching attribute works. So let's check, so it touches, doesn't touch anything. Number 6, yes, all correct. That is all correct. I wonder if I can find a case when it touches two primitives. Oh, I think I did find it. Yeah, so as you can see, the first and the second one, they touch both 0 and 2. Well, these are roof IDs, so the third one is actually the second one too. That is all correct. So yeah, so that all works. That's great. And I'll see you in the next video.
To ensure the correct stepping, we need to teach Houdini to be aware of both incoming and outgoing roof connections with the means of attributes that we are going to assign. We already determined the roof direction for the roofs that have merging, and that will be our starting point. Let's imagine we are checking the primitive, which, as you can see, has both incoming and outgoing connections. First, we will record whether it has any incoming connections by looking whether any middle line created by us earlier touches on the edges of the checked primitive. Then we will see whether the middle line of the checked primitive touches any other, except for the ones that we already labeled as incoming,
and those will be recorded as outcoming. If the roof has no direction assigned yet, we will look on the incoming connections and assign a direction perpendicular to the incoming one. If the roof has no incoming or outcoming connections, it will be assigned a direction based on its longest edge direction. So let's start implementing it in Houdini. First of all, I changed the roof pattern seek to 114 to give us more visual examples of what's going on. As here we have cases where one roof has 2 incoming and only 1 incoming. So let's also delete the sort that we used to shift the primitive numbers, as we don't need it anymore, and it's not going to affect the result. It was just for us to see what was going on in the first iteration. And let's collapse these nodes into a new subnet, which we will call roof attributes, and let's take it one directory higher, so cut it out and paste it here. So let's dive into it again. So here we have a node where we found the roof directions. Now we need to isolate the middle lines. So let's bring a new for each loop. We'll name it get middle line and set it for each primitive and merge results. So inside of the subnet, we want to isolate only the middle line if one exists, and the middle line when you use the clip node, and you want to set it for each number, and we want to go from 0 to the number of primitives that are on the input. So let's create a null and we will call it in. We'll compress these 3 nodes into another subnet, which we will call roof direction. Direction. And this middle line will take the amount of the primitives in the second input. So let's say n prims of input path of the first index and -1. So let's take that, yeah, 5, all correct. And let's dive into it. And here we would like to isolate based on the roof ID. So let's call it locate. And we say if roof ID is equal to the stamp for value 0, don't forget the brackets. I want delete non-selected, and it's a primitive. So here we have our roof with its middle line. So what we would like to do is, whenever you use the clip node, it always makes the new points the last ones in the count. So we want to abuse that by getting a blast and saying that delete everything except for the 4th and 5th point. And if such do not exist, it will delete everything. So let's call it locate middle line. And then we want to make it back into a primitive. So by group, add by group. And the next thing I want to do is transfer back all the attributes that we created. So attribute transfer from the one that we located. And we want to transfer roof ID and direction. Oh yeah, we haven't created the direction yet. So let's do it now. So attribute transfer, we'll call it roof ID. And I want to create a direction, so let's bring a wrangle node and we'll call it roof direction. But this one we will write to the point. So it's a vector attribute direction, and it's a normalized version of subtraction of positions of first point and the second one. So attribute P and the second one as well. So P index 1 and oh yeah, typed out by accident. Apply. No. Oh yeah, forgot the input one. Apply. Now we have the direction. Yep, it is correct. It is in z-axis. So all good. Let's jump back up. So the next step is we want to take our incoming primitives and we want to create an attribute with ID. So with ID, name with ID, class primitive, type integer, and the value is $PI. Next step, we want to bring in the sort, and we want to sort by vertex order. The vertex order points, yes. Let's call it sort vertex order. So now we are ready to bring everything into a for each subnet where we're going to assign incoming and outgoing connections. So original primitives go into the first input and the middle lines go into the second, and we will name it incoming and out attributes. Let's color it so we can always find it. Let's dive into it. So first things first, we want to isolate our primitive. Speaking of that, let's check it. So it should be each number. Let's first make it run only once. And here we want to say that we locate primitive. So first thing you want to locate the primitive. So let's type that we want it to be the same number as the current iteration. 0, 0. And we want to delete non-selected. It's a primitive, and we will also need to locate the middle line. So let's bring another blast, and we will say locate middle line. And here we need to say that it should be the same roof ID as the stamp, so the current iteration number. And we said delete selected, it's a primitive, and we will also need to know all the middle lines of the non-selected primitives. So also uncheck that, and we will say non-selected middle lines. Remove one. So here we have our located primitive, and we want to resample it so we can see whether the middle line touches the border. But there is one but. We do not want the corner points, because if in any case the middle line will touch on the corner points, so it does not mean that the roof is incoming. So we want to identify that case and remove it from our pool. So first we will need another for each subnet. And speaking of layering subnets, let's rename this stamp name right away. We'll call it resample. Resample. We need to do for, it doesn't really matter each number, it will always run only once here. But the reason we're creating the subnet because we will use it again. So even though it runs only once now, we will use it as a loop later. So merge results, yes, and connect, and we will call it resample. Let's dive into it, and we want to locate this again. So let's just copy locate prim from here, and we will say that it is the same, but the resample is called, but the stamp is called resample. So yeah. So let's bring the resample node. We'll do length of 0.5. Yes, we want to resample the polygon edge. Yes, yes. And the next thing we want to bring in is another wrangle node, because we want to delete the points that previously were the corner points of this primitive. So let's bring the original primitive into the second input, and we'll say delete corner points. And it's just a very small and easy code. We just want to bring in, let me do it bigger so you can see. And yes, we just want to bring this point cloud. Cloud. And you probably remember we used a PC open function. We want it from the first index. We want to grab the point position and we want to run it from the point position that we're checking now. Small radius and just 1. So if anything was found, cloud, if it was bigger than 0, that means that it found a corner point. That means that we do not need that point anymore. So remove point, remove it from the first input, so 0 index and point number. Apply. And as you can see, we're missing the corner points. That is exactly what we want. So let's go up. And so we have this resampled version. All good. And what we want now is we want to bring a wrangle node. We'll color it. It's going to be quite a big one. And what we want is we want the located primitive in the first input. We want the resampled version in the second input. We want the located middle point in the third input and non-selected middle points in the fourth input. We will call it incoming. Here we will assign the incoming attributes. So what we want to set it over primitives. We will have only one primitive, so it will just be easy to assign the attributes. We wouldn't have to write a set primitive attribute expression. We just can write at, which is very handy. Let's start. We will definitely need a point cloud, but we will also need the positions found to track how many incoming connections we found. We will also need the array of all the connections, and we will also need the roof ID import from point cloud, so import, and we will need a vector to hold the roof direction import from the point cloud as well. So let's start with the loop. For every point in the resampled version, we want to see whether that resampled version touches any middle points. So we want to import the position. So point of the resampled version, we want to grab point attribute P and point cloud, PC open. We want to look at non-selected middle lines from the position, small radius, just 1, we don't need to find a lot of them. And if something was found, then we say that found an integer is bigger by 1. And we want to import the attributes from the found point, so iterate cloud. So we want to import the direction. So direction, we want to import into the roof direction import variable. So, and I just realized that we need to go a bit up to the get middle line. And here with roof ID, we only imported it to the primitives, but we also need it in the points. So in now points, we need to say that integer roof ID equals, first of all, we need to grab the primitive it belongs to, so it's the only primitive. So we want to say that it's a primitive from the first input, and we want to grab the roof ID attribute from the very first primitive. Apply. So now we also have a roof attribute in the roof ID attribute into the points themselves. So now it will be just easier to access in our code. So let's bring it back and just copy this line and the same, but we want roof ID and roof ID. We want to append to our connections the roof ID attribute, roof ID import. Apply. So the next step is we want to record those into the attributes. So say I incoming number num equals found, and I array of incoming equals connections. And now we also want to set direction. So if and primitives, if there is no middle line, so if f primitives of 2 is equals to 0, we want to set the direction is a perpendicular, so cross of the last imported roof direction, and want it to be perpendicular across the y-axis. And in other case, we want to say the direction is the same as of the point of our middle line. So to direction 0. Apply. And we have an error, unexpected. That line 31. Oh yeah, there's a dot here. This should be a comma. All correct. So let's check spreadsheet. So incoming says we don't have any incoming, which is true. Roof ID is 0 and direction is in the axis. All correct. So the next step is to assign the outcoming. However, before we do that, we need to delete all the incoming primitives, so they're not accounted for. So for that, we will need another wrangle. Let's call it delete incoming. So we will delete it from the each. We will have all the primitives. We will track it from the incoming. We will run it over primitives, and we will say that. Let's bring it together. We will say that there is integer array that's called incoming, and we'll just grab it from the first index. It's called incoming 0, and we just say for each loop we will check every incoming number, and we say that if the primitive is the same as the incoming, we do not want that primitive. So remove primitive from the first input in num and delete the points. And we also do not want the primitive that we are checking. So we say the prim num is equals to the channel. We just create a new channel. We will call it stamp. We also do not want this primitive. So apply, create this stamp. Here it is. And we just copy it from our locate primitive. Yeah. And yeah, we just deleted the one we are checking and no incoming because we don't have them. And we want to do the same as we did with the resample, so just copy this resample. And here we want to say the same number as number of primitives. So input path -1. So now let's bring the new wrangle, and this will be the wrangle for all the outcoming ones. So let's call it outcoming, and we will follow it. So what we will need is incoming, because it holds our primitive with the attributes, and we want to continue this line down. We will also need the selected
located midline, and we also need the resampled non-selected primitives. So make it bigger, and we will run it over primitives. So we will start with creating a variable that's going to hold our outcoming primitive, and we will check every point in our line. So technically there are 2 points in our midline, so this loop will run only twice. We will need a position, so let's grab a vector position. It's position, it's point. The first index, we will grab the point position, and from the P, we will also need a point cloud, so P cloud. P cloud is PC open, and we will check our resampled non-selected primitives, so index number 2. We will also need the position. We'll check it from the position of the point, small radius, and just 1 is enough. And we say if something was found, now found, from this point cloud, we will import the attributes we need. So I think what we need, I think we have everything for now. Oh no, we need the array to hold everything we're going to import. So in, we will call it outcoming array. Now that I think about it, we should have named incoming, the connections array now incoming here. So let's do it for just the consistency sake. Connections, we name it incoming. Just easier. Incoming here as well. Incoming and easy incoming. Right? Oh, and we lost everything here. Oh, sorry for that. Let me quickly rewrite it. So yeah, so now we want to import the attributes from the point cloud. So let's iterate on the cloud, and we want to PC import, and we want to import from the cloud. We want to import roof ID to the outcoming primitive, and then we want to append this data to the outcoming arrays we just created. And we want to outcoming primitive. Yes. So apply. Yeah, spelling errors, my favorite ones. Yes. So now we want to say that the integer array attribute of outcoming is equals to outcoming array we created here, and outcoming number is just the length of this array. When I think about it, we could have done it in the previous one as well, in the incoming one, but oh well. Now you know 2 ways to do it, either with another variable or with a length function. And we just say that if this array is empty and we don't have any incoming, we want to say that there is no need for a merge, and that's a new attribute we're going to create, just an integer, and we say merge is equals to 0. However, if there are outcoming ones, we want to say that the merge is equals to 1. Apply, accept. So our primitive should have received an outcoming attribute, yes, of 1. Amazing, because it is true. So the third one. Wait a second. Why is it the first one? Problem is that our resample does not have roof ID in the points, so there is nothing to import from the point here. Probably we will have the same issue here. So in our resample, when we resample in our delete corner points, let's just say that we want this to have correct roof ID. So we just say that integer of roof ID equals to the primitive
as the first input, we want the roof ID. We just want the first primitive. Let's copy this line and bring it into our recenter as well. And now it should be correct. Now it should say the correct number. Yeah, outcoming free, so that was the error. Not even an error, just we forgot one simple line. So yeah, so that works. And the last step we want to do is we want to bring another wrangle. I'm dividing all these wrangles just for the visual purpose, so it's easier to see step by step what we're doing. But in this one we will assign direction to separate roofs. To separate roofs. Again, our primitives. So in this one, sometimes we will have square primitives. In that case, we need to make a random decision of the direction. So in that case, we will need a seed. So let's bring it bigger. And we'll say float seed is primitive number plus the endpoints. Technically, we will always have 4 points. So let's just create a channel, call it seed, and we say that if incoming number plus outcoming number are equal to 0, so it doesn't have neither of those, then we need to check the which direction. So we say we want to access the points, so PTS frame points and frame number, but we could just write 0 as well because we will have only one number. That does not matter. And we want to grab all the positions, well, almost all the positions. We want definitely the first point. PTS 0. We will need a second point. Let's copy this. And it's PTS number 2. And we will need a third point. Just copy all this line, paste it, and it's the third point. But we don't need the fourth point because we can determine the dimensions with only 3 points. And then we say that we want direction 1, which is P2 minus P3, and the direction number 2, P2 minus P1. Yes. And we want to have the distance. So distance 1 is distance P2 and P3, and another distance 2. It's a distance of P2 and P1. So we say if distance 1 is bigger than distance 2, the direction is a normalized wow, my spelling today, I'm really sorry about that. So normalized direction 1, and else if distance 1 is the same as distance 2, which means we have a square primitive, then that's where we need to use our seed. So we say random of the seed we have is bigger than 0.5, we're just going to have 50-50 chance. We say the direction is normalized, and I just realized that here I wrote actually normalized. Yeah, so normalized direction 1, and in other case, just copy, we just use direction 2, and here we also will need to write it else if the distance is not equal to distance 2 and the distance 1 is not bigger than distance 2, then the direction is normalized version of direction 2. Apply. And syntax error, I'm not surprised. Unexpected bracket. Line 4. Oh. Apply. Another syntax error. Oh yeah, I put square brackets. So yeah, let's apply, accept. We have an assigned direction to separate roofs. So let's test it. Let's say that we want to run it over all the primitives in first input. And let's check. Let's check the spreadsheet. And let's do it together. So the first one, in primitive number 0, outcoming 3, correct. The first one is outcoming 2, correct. And the fourth one is outcoming, beautiful. Then incoming. So the second one, 4 and 1, correct. And the third one is 0, everything doesn't have an incoming. Beautiful. Do we have any separate roofs? Yes, we have the fifth separate roof, so it should have received a random one. So direction is, we decided to go with Z, that's correct. And the third one didn't have a direction, but now it goes with X. Beautiful, everything works. And that's it for this part. And I'll see you in the next video. Hello and welcome to the next video of chapter 1. And here I'm going to explain you our next step, which is assigning heights to our roofs. So we're going to start with the corner primitive. So let's imagine this is our starting point, and we're going to assign it an initial number that is going to be our point of reference. Let's imagine that our corner roof height is X. And then we're going to look at all the incoming and outcoming roofs. So the outcoming roof has to be higher. So we say that it has to be higher by 1 step. So it will be X plus 1. However, the incoming roofs, they have to be smaller. So we say it's X minus 1. And then we check the next roof. Let's say this is the next roof. And we say, aha, it has an outcoming and it is already bigger. So we don't have to modify this. And we have also another outcoming, but it hasn't been assigned anything yet. So we assign it something plus 1. So it's X. However, if we check this one right now, we're going to check, yeah, one of the incoming is smaller, that's correct, but another one is bigger. This means that this bigger number, we have to have this one even bigger than this one. So we say that, no, it is not X, it is X plus 2. And it would be the same if, for example, we had an incoming roof here, and it would be something like, in the loop, it got assigned something like X plus 4. Then we have to modify this number again. So that is the basic strategy for assigning the heights. So let's implement it in Houdini. So let's start by creating a height attribute. So let's grab attribute create. And we're going to call it height. So name height, class primitive, type integer. And it should start with a 0. Then let's sort our primitives along a vector, not point, primitive along vector, and then point, no change, primitive along vector, and this vector should go in both X and V. So we will always get the first one as a corner that progresses through the bounding box shape. So let's say sort by vector, and let's grab a for each subnet. We're gonna call it height assign loop. Let's make it each number. Start with a 0. For now, let's make it run only once so we can control it better, and merge results unchecked, because our iteration loop will be based on the previous results as well, as we need to access the attributes that were previously created in each iteration. So let's dive into it. And here, all we will need is a wrangle node. Attribute wrangle. We will call it height assign, and we need to run it only once. So let's make it bigger so you can see everything. So we will need a lot of variables. So first of all, let's create incoming list that is equal to our previously created incoming list attribute, incoming from the primitive. And let's identify the primitive. So what primitive do we want to check? Well, we want to check the primitive that equals to the number of current iteration, which we're going to grab with the channel. So let's create channel. We'll call it primnum. which we're going to identify later. So let's also grab an outcoming list, which is the same. We just grab it from our primitive. Outcoming primitive. So let's apply and let's create our channel. So here's our channel, prim number, and it's just stamp. The same way we write it every single time. So for value, 0. So currently it's going to be 0 because we run it only once. Implicit cast from float to integer. Oh, it complains about our channel, so specify that it's channel I. Let's create it again. It's going to create a new one or not? No, it's going to just replace. Implicit cast from still. Added parameter interface. Yeah, it's for some reason it still sets to float, so I guess let's edit it manually. Apply, accept. Oh, we haven't applied it because why? Channel I, yeah. So yeah, if you say channel I, it will create an integer channel right away. So now we're not going to have any warnings. No, great. So we will also need to know what is the height of the current primitive we're checking. So let's create height attrib, and we will grab it also from the primitive, from 0, height, and also from the primitive. Now we will check whether there are any incoming faces. So int incoming primitive from the incoming list that we just imported, and we want to check all the incoming heights. So incoming height is primitive 0 height from the incoming primitive. And we will also need it to store it. So let's create 2 lists. We're going to name them incoming heights and outcoming heights. And we'll append this height in our newly created list. So incoming heights, incoming height. So we need to find which is the maximum incoming height. So first of all, we need to check whether there are any incoming heights at all. Maybe we don't even have any incoming faces. So let's check if length of our incoming list is bigger than 0. We say that if maximum of the incoming heights is bigger or equal to our height attribute that is currently in our primitive that we are checking, that means we need to modify the height attribute that we have. So we say that then the height attribute is the same as maximum of the incoming height plus 1. So for example, if we have an incoming roof of x and our roof is also x, that means that the incoming has to be smaller, but instead of modifying the incoming, we're going to modify the face that we're currently checking. So sorry, my recording software stopped recording because I ran out of space, so we lost just a tiny bit of progress. So I'm just going to walk you through it. So we stopped at checking out the outcoming faces and their heights. So we grabbed the outcoming heights from the outcoming lists, and we checked the outcoming height to the height attribute. And if the outcoming height was not bigger than its incoming roof, we set it to a new primitive attribute. So its height would be the height attribute plus 1. So we set that, and now we just need to check a new case. We need to check what if there are no incoming or outcoming lists. Like, we don't want to keep it at 0. We want also to make it random, and it doesn't matter whether it has neighbors or not. So we say if length of the outcoming list plus length of the incoming list is 0, which means both of them are empty, we say that we want to create a new height attribute, to create a new value of the height attribute, and we want to grab random of the primitive number plus number of the primitives. This will just give us a unique random seed, and with every iteration, like we're going to have different number of primitives, so that should work perfectly for the random seed. We want to fit it from 0 to 1 to 0 to 4. And why 4 is, just trust me on this for now, because later we're going to convert the platforms, and the maximum amount of platforms we will have is 4. So just put this number for now. Trust my word. I'll explain it a bit later. So don't forget to round what we have, because we just need the integer, and don't forget to convert it to the integer. And after you have this new value, set primitive attribute, the height attribute of the primitives that we are checking, and this new value, the random one, just set it. So accept. Once you go up, make sure that the number range goes to the number of the primitives of the first input, so n prims of the input path. So we run it as many times as we have primitives. And don't forget to delete the sort that we created, because turns out it messes up with our roof IDs, as previously our roof IDs were the same number as the primitive number. But once we sorted, our numbers in the list do not correspond to the number of the primitives anymore, which really messes up with our code, because our code heavily relies on having the correct primitive number that it's checking. So do not sort. Sorry so that I confused you and made you sort it first. We do not need it. So after that is done, we need to check a special case, which I'm going to illustrate you. So here are my previous scribbles that I made. And let me make it a bit bigger. So sometimes we can have a very special case. Yeah, when our roofs have directions that go in a loop. So if this one is x, this one is x plus 1, this one will be x plus 2, x plus 3. But hey, this x plus 3 has an outcoming the smallest, so this one will be x plus 4, this one will be x plus 5, and endless. It will endlessly go around. We do not want that. That is why we will create an additional safety check. It's just going to look for this kind of errors. And if it finds that error, it says, okay, this roof has an error because its outcoming is smaller than itself. So what we want to do is we want to convert this roof into absolutely new separate floor. So if we have this case in perspective, we will just create a new floor. It will be absolutely independent from all the other roofs. And this roofs will be just like on the lower level. So this is the roofs. So that is the plan. So let's implement it in Houdini, or should I say, I will show you how to implement it because it's already written. So, and by the way, I started commenting on the notes. Previously, I was doing it off camera, so if you're ever lost, just check the files I included, and they all have comments and explain what to do. So just grab a new Wrangle node, call it check for height conversion, set it over primitives, and here we want to grab our outcoming list. Technically, you can check incoming as well. It truly doesn't matter which one you're checking, because the only thing we're looking for is for the error. I decided to grab the outcoming, so outcoming list. We grab it from our primitive, so in integer array of the outcoming attribute. Create a new variable called outHeight, and make a loop that runs over the outcoming list with the outP integer. Identify outHeight, just grab from the primitive the height attribute from the primitive you are checking with the loop. And if that height is not bigger than the height attribute of our checked primitive, so our checked primitive is bigger than its outcoming roofs, that means that our primitive has to be converted. So we create a new attribute called convert. It's going to be just a boolean 0 or 1. So in this case, it will be 1. And we want to also empty the outcoming and incoming lists, because this primitive will no longer have neighbors. It will be separate entity on this next floor. So apply, accept. I also created visualizers in D. I created a new marker, height. If I can edit it, duplicate, delete, not sure I can edit it. But yeah, I just created a new marker and I just set it to attribute of height so we could see. And as you can see, it works perfectly. So this one will be 1, 0, 0, 0, 1, 0. So that all works perfectly well. So now let's determine the elevation of our roofs. And the way we're going to do it is, first of all, we need to find the widest primitive. But there can be multiple, so we say the widest primitives. And among all these widest primitives, we need to find the one with the smallest height number. And the reason for that is this is going to be our reference of elevation. And why are we picking the widest and smallest in height primitive? Well, the reason for that is that sometimes we have very wide cases. So let's imagine it's like 4 modules width. And if it's not treated first and it's being assigned based on the other primitives, it can get very small elevations so that the roof is like super small. Or on the contrary, it can become very big and just like a huge castle tower, which we don't want, because usual roofs values, there's something between 30 and 60. Like this is the most common angles, the most like extreme one, because 30 and 60 is already kind of extreme. Most of the roofs you see are probably 40. And if we have numbers that are smaller or bigger than 30 and 60, the roof will just look very odd. And the chances of the roof being very odd on a very wide surface is higher. That is why we're going to determine its elevation first, and it will drive all the other elevations. And how are we going to find the elevation? Well, let's imagine that the roof is somewhere here. And how are we going to do that? So you probably remember from high school math classes that you can find, let's bring another color, like orange one. We can always find one of the sides of a triangle with a 90-degree angle based on the other angles that we know. And we do know, let me pick another color. We know this angle because we know what angles are possible for this roof. So based on that angle, we're going to find our elevation. So, and there is a very simple formula, and it's a tangents of our angle, and we need to multiply it by width divided by 2. So why width by 2? Because this is our width, and our point from where we go up is the middle. So if this is the whole width, then it's a width by 2. And this is the same, width by 2. That is why width by 2, because that is another side. And by multiplying the other side on the tangents of this angle, we will get our elevation. So, elevation. So, but what do we do after we found our reference elevation? Well, that is very simple. Let's imagine that we have, in total, we have, I know it's a very big system, let's imagine it has like 5 different heights. So it can be 0, 1, it goes all the way to 2, 3, 4, and 5, like it's quite a big one. And we need to find an elevation number for each of them. And I don't know, for example, our elevations we found, the reference one is somewhere like here. It's like the 4th one. So what we do is we say, okay, great, we already know the 4th one. So let's call it E. And it's the index 4. So now we need to find the index 3 and 5, and it's quite easy. We will create a loop that will go 1 index up and 1 index down. And what it will do is from for the down one, it will subtract a random number. And from the up one, it will add a random number. And it will do it so on until like the list ends. So if this list wouldn't end on 5, it will go further. And this way we ensure that all the smaller indexes have smaller values in our reference, and all the up indexes have bigger value. And no matter where this E starts, like on 0 or 1 or 2, this will always work. And this is how we will find our main list of elevations. And then we just run over the primitives and we just assign. So like when we have a primitive, we just check, okay, this primitive, is it like number 2? Okay, then it has like E minus X minus Z. Or is it like 5 and it has E plus Y? So very simple. We will write it with vex. And so let's dive into Houdini. Since we already have the height attribute, we can identify the maximum height by taking an attribute promote, which is here. And we're going to call it max height, which stands for maximum. Original name is height. It's a class of primitive. We will promote it to detail. And the average, we don't want the average, we want the maximum. And don't delete original. We will change the name and call it maximum height. So max height. Good. So now we need to get sort. And we need to say vertex order. To sort points by vertex order. Because now we're going to grab the width, for which we will need the subnet. And we will call it width attribute. Oops. Yes. And it's for each number, not for each number, sorry, for each primitive. So when we dive into it, we have only one primitive. And here what we're going to do is we're going to grab an attribute wrinkle. We're going to say it's a width attribute. And we'll run our primitives. So we have only one primitive, but it's just going to be easier to assign the attributes. And here what we want to do is we want to grab 3 vectors. So vectors P1 is going to be our first point. It's point number 0. And we want to grab 3 points. So 2, 3, and here 1 and 2. Right? And now we want to get their edges. But not just edges, but the direction. So vector edge 1 is P2 minus P1, and vector edge 2 is a P3 minus P2. But we want the absolute version because we're just going to compare the general direction. We don't need to know whether it's negative or positive. And we're going to compare it with our direction. That is the attribute. So it's a vector attribute. And we want a normalized version as well. So normalize, and we want to normalize actually everything. So let me copy normalize and grab it here, and one more bracket. Yes. So we say if edge 1, even the rounded version of edge 1, equals to the rounded version of the direction, that means that this edge is parallel to the direction, which we don't want. Then it means that our width is a distance between P3 and P2, because then if this edge is parallel to the direction, that means we need this one, and we need the width of this edge. In the other case, we grab the other edge, and it's P1. Apply, accept, and let's check. Spreadsheet, and the width is a 2, 1 is a 4, 1, 1, 1. Yes, correct. Everything else is a 2. Amazing. All this works. So next thing is we want to get the maximum width. Like, what is the maximum width? The same way, we get the attribute promote. We call it max width. As a class primitive, we will promote it to detail. The width, we want to keep the original, and we want the maximum one. Change the name to maximum width. So after that is done, we want to create a couple of attributes. So let's create attribute create. which we will need in our loop, we will assign the elevations. Init elevation attributes. We will need 3, I think. Yeah, 3 overall elevations. So we will store here an overall elevation of how high this roof has to be in total. And it's a primitive. We would also need the elevation itself of only the roof, because we can also have a platform. So platform elevation can also be the case. So technically, overall elevation equals to elevation plus platform. So now we are ready to create our big, well, not big, but the main loop for elevation. So let's call it elevation / platform. We will run it only once. And let's make it bigger so we have a lot of space to write, because we will need quite a bit. And let's comment right away. So we say that the first step is find all the primitives with the maximum width. Like in this case, we have only 1, but sometimes it can be the same. For example, the maximum width is only 2, and we just need to find all of them with that width. So we will need to grab maximum width, first of all. Otherwise, how else we're going to find it? So let's grab the detail of our first input, which we called max width. We will record all those primitives we're going to find. Oops, I missed. Yep. So we will need a list to store all of them. So we'll call it max width prims. Oops, prims, yeah. And we're going to access in the loop. We're going to run all over the primitives, and we will find each single one of them. So primitives, all primitives. And in the loop, we will also need integer. So let me grab this width here, because we're going to grab the width to compare it to. So primitive, the first input, we want the width of the PR. And we say that if width is the same as max width, then we want to append the width max. So we want to append to the maximum width primitives PR. So after we did that, we want to find the primitive with the smallest height number among the maximum width ones. So, well, first of all, we want to check whether we even have to do that. So if the length of our list, so max width prims, is bigger than 1. But before we write the loop, we will also need to create the list. So in integer here, let's create a heights list. And this heights list, we will append all the heights right away. So in the width, we will also need the height. And here, if the width is the max width, we will also need to grab the height. So we will grab the primitive from the first input, we will need to get the height from the primitive, and we will also append it to our heights list, and we append the height. So yeah, that is important, because here we're going to access it again. So if we have more than only one primitive, then we make a loop, and we say I for index, and we're going to say that the index is smaller than the length of the heights list, smaller or equals, and I plus plus. And so we say if heights is of I of the index is equals to the minimum from the list of the heights, if it is indeed the smallest value, we say that we found the select prim. So let's create a variable for that. We will call it int selected, or let's call it reference prim. So the reference prim is the maximum width prims and the same index, because the indexes of our height list and the width list correspond to each other. So apply. We missed somewhere. It was 23 heights list. Oh yeah, I put a comma here. Sorry. So apply, accept. Oops. Apply, and it says heights. Heights. I remember. If heights. Oh yeah, heights list here. So apply. Yeah. So that is only if our length is bigger than 1. If not, very simple. We have the only primitive. That means it's the height of the minimum height is that only primitive. So we say that the reference primitive is max width prims and the very first one. So then we say, based on the reference primitive, let's find roof elevations. So we will need a new variable, elevation, and it's a float because it can be any number. So now we need to decide how are we going to do that. We have the formula, I already explained to you in Photoshop, but we need to determine what angle we want to give it to. And what I found that works is that we need to make sure that based on the width, we're going to assign it kind of different ones, because when you have a very wide primitive, you don't want the angle to be too big. Otherwise, the roof is just going to look like a tower. So you want to make sure that we have different numbers for different cases. So we will need to say that first of all, we need to grab the width. So we say that the width, the reference width is primitive width, and it's our reference prim. Let's actually make it ref prim rather than reference, otherwise we're going to write a lot of extra letters. So reference, yeah. So we say that if that reference width is smaller than 3, then our elevation. And here, before we write what our elevation is and we write the formula that I wrote down in Photoshop, I want to create a function, because we're going to call this function a lot. We need to convert our elevation angle to the elevation height. So before we write this, we apply it. In the very beginning, let's comment it out even so we can see that there is a break. We will write a custom function. This function is a float one. We will call it get roof elevation. And what we need is just an angle. And we need the width, as you remember from the formula. Oops, not semicolon. Yeah. And here we say that the float height is a tangents of the radians, because it calculates everything in radians. And we multiply it by the width divided by 2. And we return the height. So now, apply. And then expected. Oh yeah, not a comma but semicolon. Apply. And here we say that our elevation is get roof elevation angle of 50 and max width. Oops, not max width. Reference width. Well, yeah, technically, our max width is the ref width, so we don't need that. So sorry about that. Just say maximum width. Maximum width. Else, it's an extra R here. So elevation copy, else if it is bigger than 3 modules, then we want it to be 40. So yeah, after that is done, let's assign platform and elevation for the reference prim. Since we already know what it is, why not assign it right away? So set primitive attribute, first input, and we assign all the created attributes previously in with our attribute create node. So overall elevation of the reference prim is equal to elevation, and just set. Let me copy that, and we say that elevation of that reference prim is elevation, because we're not going to have any platform for that one. That is why we were also looking for the minimum height, because we want to calculate this one based on no platform additional height. So elevation, here is a platform, and platform is just 0. Apply, that is all good. And now we need to make a list for all the elevations. Make a list of elevations per height level. So let's create a list for that. So it's going to be a float list. So elevation per height list. We will need the maximum height now. So maximum height. So we know how big our list is going to be. So detail. And it's from the first input, maximum height. We will also need to know the height of our reference prim. So ref prim height is primitive. The first input, we need the height, and it's a ref prim. And we will need to append this height to our list. So elevation, and we will append the elevation that we already have, our reference elevation. And for the loop, we will have 2 integers, minimum and maximum, and we can already assign their value. So the value is ref primitive height -1, and maximum is ref primitive height +1. So we're going, like, as I showed you previously in Photoshop, we're going to step up and down. So then we need a float for random elevation. And we will also have a minimum loop elevation. So that was, for now it is just the same as elevation. And float maximum loop elevation. And it's going to be as the same elevation. And from those numbers, we will subtract and add a random elevation. So now let's create the loop. We will call J, and let's say that J goes. I don't think I will have a list bigger than 20, so let's say 10, because at each loop we're going to make 2 steps, so 10 and G++. And here we're going to check for 2 things. So we're going to check for maximum. So we say if maximum is smaller or equal to maximum height, so we haven't reached the end of our loop yet on the top border, up border, then we say that maximum is bigger by 1. And we say that random elevation is a random of the J plus... we will need a seed for that. So let me create float seed, and it's a channel, and it's a seed. And we will say that it's plus seed plus something from the input itself. So let's say endpoints first. And we say that this random, so let's check it first. Unexpected semicolon, yeah, it's here. 79. Yeah, it's 1 extra. Yeah, that's what I was trying to check. So yeah, now we say that we want to fit this random elevation from 0 to 1, from 0.2, which is our minimum elevation, to 0.5, which is our maximum elevation. So apply. And then we say that now the maximum loop elevation is bigger by this random elevation. And we append to our elevation per height this maximum loop elevation. The same way we're going to check the minimum. First of all, we need to see whether we can go down. So we say if minimum is bigger or equal to 0, then minimum is minus minus, so it becomes minus by 1 step for the next loop to check. And we say that random elevation is, and we're going to just copy this, paste it here, and we just create a slightly different seed. So we say to our seed value +7, so just a bit different. And we say that minimum loop elevation is smaller by this random elevation. And there is a function which is called insert. So we're going to insert this value into our elevation per height, and we're going to insert it in the very beginning of our list. So to the index number 0, we're going to insert this number. So minimum loop elevation. Apply. So yeah, we created the list. Let's see how it looks. Let's say printf, and we're going to say that it's a D and N, and we want to see two things. Let's see our reference, and let's see our list. So I want to see the reference. So let's say it's our max width. We kind of know the maximum width is 4, so we don't actually need to see our reference. So let's delete that. So our list, I want to see what kind of values it made. So let's say that we want to see the elevation per height. Apply. Accept. So it should show us the, yeah, here it is. So that is our list. Why do we have only 2 numbers? Well, because we have only 0 and 1 elevation heights. So everything that has a 0 has an elevation of 1.67. And everything that is 1 is going to have an elevation of 2.07. So now, let's delete the print. Say based on the height of the primitive, assign it the elevation value. Oops, elevation value. So here we will need to import the height. So we say height import. We'd also need to know the roof width. So let's actually say width import. We will also need to get a variable where we're going to record the roof elevation, so prim elevation. And we need a vector of roof heights. And why a vector, I will explain you in a second. You're going to see. In our loop, where we're going to check for every primitive. So primitive is, let's call it prim equals 0. Prim is smaller than all the primitives. Prim is bigger by 1. So here we're going to import our height import. I'm going to say it's we grab it from the primitive. So prim of 0, height, and the prim. The same as width. Width import, prim, 0, width, prim. And now we will need to write another custom function. So let's go all the way up again. And here I'm going to say that this is a vector function. That is why we created a vector, because here we will need to return multiple values. That is why I created a vector. So we call it additional height. And for that we will need to know the float width, float elevation, and number of the primitives. So int prim num. So here, since our roofs can only go from the angle of 30 to 60, it kind of limits the height of the roof. And if our roof exceeds the maximum height that is determined by its width and 60 degrees, it needs a platform. So that is why we will create a maximum height, which is a get roof elevation. We will see how big the roof can be. So 60 is our maximum, and we will see based on its width how tall can it be, because for every roof it will be different. As well as we want to see the minimum height. So we say get roof elevation, and the minimum one, 30 degrees width. And then we will create a variable of a platform. For now it will be 0, so non-existent. We say that float roof elevation, it is the elevation. And this, what we say, if maximum height that is allowed is actually smaller, so let's actually rephrase it. If elevation that we have is bigger than the maximum height that is allowed, then we say that our platform is an elevation minus max height, so we see by how much it is bigger. But we want it in steps, because all of our platforms, we want them in the steps of 0.2, because it will be easier later on to generate geometry for it. So we say that it's a rint, and we do the same trick as we did for the grid when we constrain the points to the grid. So we will say multiplied by 5, and here we just divide by 5. So it will always be a platform of 0.2, 0.4, and so on. And we say that if platform is smaller than the elevation, because it has to be smaller, otherwise it will cover the whole thing, we say that the roof elevation is elevation minus platform. So the roof elevation itself, is what is left when our total elevation got subtracted by platform. Else, if the platform covered the whole elevation, we don't want the whole roof as one big platform. We just say that platform, just don't do it. Platform is 0, and roof elevation is the elevation. And then we need to check, is this roof converted? Like, because remember we have the special case where we converted the roof to an additional floor, and then we say int convert, and we just import it. We say that oops. Is from the first input we want to the convert attribute, and prim num. And we say that if convert is equals to 1, platform is 3, because 3 is the height of one floor. So technically we kind of made the platform as big as our one floor. And now we just want to return this two values. So we say in a vector. So we just say set. We want to return the roof elevation, as well as we want to return the platform, and nothing in the third one. That is why it's kind of like a small trick, because I need to return two values, not just one. So we just included them in a vector. So apply, and we'll go down. And so here we say that the primitive elevation, so a roof elevation, is elevation per height. And yeah, we want to grab the roof elevation, like total one overall. So we need to know what is the elevation of this level. So we need to say that elevation per height, and as index, we just use the height import, because technically it acts as an index. And now we can grab roof height and roof heights, because it's our vector. And we just say additional height, and we need to input the width. We need to input the elevation, and we need to input the primitive number. So we did all of that. So apply. We have a mistake somewhere there. 7, 7, 7, 7, 7, 7. Oh yeah, semicolon here. No need. Now what is else? 141. Roof width. Oh yeah, sorry, I forgot we renamed it. It's a width import. Sorry about that. So yeah, all good, all works. And now we will set the primitive attribute. and that we say that we want to set the elevation. Let's start with the overall elevation. Oops. Overall elevation of the primitive is the primitive elevation, and it's set. Then we want to set primitive attribute to set the elevation of the roof itself, so prim, and it is our roof heights, and it's the first index of our vector, and we set it. Just copy this line, paste it, and here we just need to change the elevation to platform, and it's index number 1. Apply, accept. So I don't think we're gonna have any platforms in this case, because, oh, actually it created us a platform. Interesting. Okay, so we do have actually a platform. I guess it was determined randomly. And elevation itself is, yeah. You can see that elevation itself is very similar. However, these 2 and 3, they have platforms. So 2 and 3, they will have platforms. However, the elevation of both roofs, like the angle of the roofs, is very is almost the same. Yeah. Let's color this node. And now the last thing, because there is another special case, but which refers to the platforms. So let's grab a Rango. We will call it special platform case. And the special case is, we're gonna run our primitives, yeah, is when we have 2 roofs of the same direction, and one roof kind of merges into the roof of the same direction. In that case, we want to make sure that there is no platform difference, because if there is a platform difference, it will just look plain ugly. We want to make sure that this roof that merges into the outcoming roof of the same direction has the same elevation and platform. So let's say if the outcoming roof has the same direction, and we say that, so we need a platform of the outcoming roof, and we need the direction. Oops. So for each int out, we're going to check all the outcoming ones. So we need to access the array. And we say that the direction is primitive 0 direction of our out. So out, which means outcoming. So if an absolute of direction of the current primitive that is being checked is the same as the absolute direction of the outcoming direction, we need to grab the platform number. So our platform number is a primitive platform attribute, and it's of the outcoming one. And we say that if platform is not equals to out platform, so they are on different platform levels, we need to make sure that is not true. We need to say that the platform is the same as out platform. Apply accept. Okay, so that is for this video. In the next video, we're going to extrude our roofs and make the merging. But for now, we have everything prepared to actually start seeing finally the fruits of our hard work and to see them visually, because for now it's just been these numbers, but we will finally soon see the visual result. So thank you for watching, and I'll see you in the next video. Hello and welcome back. In this video, we're gonna finally see the result of our hard work. We're gonna see the roofs finally taking some visual shape. So let's just start. We will need a for each subnet, which we will call roof extrusion. And it has to be for each primitive, merge results on, and inside. turn it on, and inside we will need to do two things. First one is that we need to clip it again. We need to assign it the direction again. So let's bring in clip. We want to keep all the primitives. We will say clip direction. The origin is just the centroid of this primitive, so of input path of index 0, and we want to grab the dx, and we want to grab the dz. Y doesn't matter, and the direction is primitive, so we're going to access the attribute direction. So we say that it should be from the first primitive, it's called direction. We need to grab the z in x and x in z. Oops. Copy this one, paste it here, 0, and direction y should not be there. So here we are. And that's our direction right there. And what we want to do now is we want to take only these points and we want to pull them up on the elevation attribute value. So let's bring in transform node, connect it. We want to say that the group we want only P4 and 5. So this edge 4 and 5. It will always be the same because when the clip creates new points, they are always the last in the point number count. So in transform, just say that we want to access the primitive again. We want to go to the, well, actually we can just go up input path again. Of the first primitive, we want to grab, we want to grab elevation. So here we are, we have the elevation. But some of our roofs have not only elevation, but platform as well. So for those cases, so the transformer node, let's rename it to roof elevation. And then we will just simply copy it. And we will call this one transform platform. So we're going to put everything up, not only points 4 and 5, everything up by the amount of the platform. So here we just replace the elevation with platform. So yeah, this one doesn't have a platform, so it's just a 0. And yeah, and the platform itself we will generate a bit later. So let's go up. So view, and as you can see, beautiful. All of our roofs are absolutely amazingly merging. Well, not merging yet, but they're all in correct relation. And I really like how node like this roof looks very, like has very sharp angle, and this one is just different shape, and it's merging with this one, and this one is on a different height level a bit. I just really like the visual outcome of this algorithm. So to give you a bit a better idea, let's actually merge it with our body base. I think that you can better see. Oh, yes. Let's turn off the primitive numbers, and yeah, just look at it. Very, very nice. This is our half balcony. Oh, beautiful. Okay, so let's go back to our roof base. Our work is not done yet. Okay, so let's collapse it into a subnet, which we will call roof extrusion. And F. If you're ever lost in this view, just press F. It will zoom you on the nodes that I selected. So in here we will need a new for each subnet, which we will call roof merge and sides. And we want to run it as many times as our input. So this one, let me show you. No, let's call it N. So yeah, because we want to run it for every roof. So here it says that we want to run it each number, and for now just make it the 0 one. And we want to merge the results. Yes, that's all good. So let me check which one is the 0 one, because I want us to have a visual example. Yes, this will have a visual example of the merging. That's good. So yeah, let's dive into it. So here we want to locate our roof. So let's bring blast. We will name it locate, and just do the same as we did previously. Delete non-selected, and we want roof ID to be the same number as current iteration number. So stamp for value 0. Yes, that is our roof. So the next step is we want to find the outcoming roofs. So let's bring a wrangle node, attribute wrangle, and we will connect this one to the second input and each to the first, because we're going to find it from the each based on our selected roof. We will say get outcoming, that's how we're going to name it. We will run it over the primitives that we have, and we will write a bit of code. So let's bring bigger. Here we start. So we say that there is an outcoming list, which we will grab from our primitive that we selected with blast. Outcoming. Then we need to find the correct primitives that are gonna correspond to the numbers in the list. So we need to make a variable found, and then we will access the loop. We will access the list through for each. So int I in our outcoming. Let's call it actually out. Makes more sense. And we say if roof ID of the primitives that we're checking with this loop is the same value as our out, then found plus plus. And if technically once we found it, that is the 1. And if found equals to 0, and by the way, here we can break the loop because it will never be found more than once. So let's say break, so it just doesn't run it unnecessarily more times than it needs to. And we say that if found is equal to 0, which technically means this is not a part of our outcoming list, we don't need this primitive. So we say remove this primitive, we say bind to it, we say that it's a prim num and bind to its points as well. So apply, accept, and as you can see, we successfully located our outcoming roof. In this case, we have only 1. So the next step is that we want to correctly merge this point, point number 4. We want to array it on the surface of this roof. So let's bring another wrangle node, attribute wrangle. We'll call it normals and array, because we're also going to make normals. So in this one, we will modify our located roof. We will need the information from the get outcoming, as well as we're going to also check for the intersection with the body. So we will need to take the body as well. For that, let's go up. And here is our null. We will say that it's called in, because I think it should be our body. That is correct. That is our body indeed. We will connect it to the roof extrusion. And here we will bring it to our third input. And here we will also bring it here. We say in body. Third one. And we also want to make a peak, a very small one, because when points have like the same position, it will not account correct intersection calculation. So we just need to offset it a tiny bit, and just like something very small, so minus 0.05, just a tiny bit. And this will go into our third input of normals and ray. So here we need the points. So first of all, what we need to do is we need to find whether the top points intersect with outcoming roof. For that, we need to find the direction in which we have to array them. And to do that, we need to find its other neighbor. Like, for example, for this point, its other neighbor of the same position y will be this one. And by subtracting the positions, we will find the direction that will continue the line from 5 to 4. And for the point 5, it will be a line that continues from 4 to 5. So let me show you how to write that. I think it will be more clear when we write it. So we say that we will need an array for the neighbors. So neighbors, it's a function that will return you the list of all the neighbors of the point you are asking. this function will return you the array of all the neighbors of the current point. So we will also need a variable for the final neighbor. We will need to access their position because we're going to compare by the position in Y. So let's let's comment it out, and we will say that look for the neighbor of the same position in Y. So we're gonna do it with a for each loop. We're gonna access every component of our neighbor list. So let's identify the position. So it's point. We'll grab the point position and we need from our neighbor. And we say that if position Y is the same as our position of the point we are currently checking, then the final neighbor, the real neighbor, is indeed the one we're checking in the loop right now, and we don't need the loop anymore. We can break it. And we say that the normal is a normalized version of our position minus the last position that we identified here, so it will be the position of this neighbor. So let me show you what it means. So as you can see, they all point in the opposite direction of its center. And that is exactly what we need, and we will also need that for the placement of the modules. So we need it not only for the points that we're going to check right now, but for all the points, as this will drive the placement of the modules later on in the system. So after we did it, let's say that now we're going to check for merging. And then we say, here we only want to check if the point number is 4 or if the point number is 5. So we only want to check the top points. So here we will need a bunch of stuff we're going to check. First of all, we're going to check for merging with the roof. We also need to check for merging with the roof of the same direction, because when the roofs are of the same direction, we want to find the point to lie on the roof, so it's like a continuation of the roofs. So for that we will need 4 intersection checks. Let's start writing. We will need a lot of vectors, a bunch of them actually, for all of this intersection checks, and PV3 and UV3. So, and then we will write all this intersect functions. So the first one is we want to check the roofs. So we will go to the first input. We will check it from the point position, and it's the normal that we just created multiplied by 10, just so it's big enough to actually intersect. And PV UV. And we say that this one is check for roof merging, and it's called inter1. So let's copy this line. No. Copy this line. And we say that then there is another intersection we want to check, and this is for check for roof merging of the same direction. So here we say that we want to check it slightly offset. We want to offset it a bit forward, and we just want to ray it down. Yes. And the last one, but not least, is we want to check for intersection with the wall. And it's just normal. You don't have to multiply it by 10. And it's input number 2. And here, don't forget to set PV is 2, UV is 2. Oops. And here, PV is 3 and UV is 3 as well. So apply, should not be any mistakes. No, amazing. So now we need to write lots of conditions because we want to write a condition for each one of them. So bear with me here. So lots of ifs. So if intersection 1 happened, so it is not false, then we want to know the distance. We want to know where exactly this intersection happened. So we will need a float. We will call it dist, just the distance. And we want the distance between our current point position and the point of intersection. That is why PV is important here. And we want to say that, okay, now just transforms this point position that is actually merging in the direction of its normal that we created, multiplied by the distance. So because our normal is normalized, it will technically go in the normal's direction as far as our distance is. And we also want to say that it's a ray point. It's an important attribute which will drive also the placement of certain modules. So it's important to state that it is a ray point. And once you found it, we want to access its neighbors again. And 2, nice. And here it's gonna be like a safety thing, because sometimes if you only transform the top point, you're gonna see holes, because the bottom points stayed on their places, and sometimes the roof can have a platform or not have a platform, and is it gonna be just a break? So we need to make sure that it also intersects. So we will need a fourth intersect. We call it inter 4. Oops, inter 4. And here we just identify it, but here we actually going to use it in our for each loop. So we will need to grab the position. We're just going to rewrite the position we already have, because we're not going to use it anymore. So why not just utilize it again? And we say we want to grab the point attribute of our neighbor. And we say that if position.y is not equals to the position of our current point, which means that these neighbors are the bottom ones. We want to say that the inter 4 is basically the same thing as this one. So copy that, but we check it from their position. We check it from the position of the point of the bottom neighbors. We check from their position. I want to see whether they intersect with the roof as well. And if there is an intersection happened, we want to make sure that they'll stay on that place. You want to make sure that they transformed to that position. So inter 4, if it's true, so something happened, you want to set point position of our neighbor to this PV set. And note how we also utilize this PV and UV of this one, because we already used it and we're going to use it again, so we just utilize this variable. So apply. We have some mistakes. Oh yeah, I already see a misspell. Intersect, apply. And here let's comment it. Let's say that check whether the bottom points also intersect with the merge roof. Apply. Okay, so next stage. Then we check what if our intersect 2 is true. But we only check it if this one wasn't triggered. That's why else if, and not just if. So if that was true, we need the distance again. So let's make a second distance. We say that it's a distance between this point plus the one we wrote, the offsetted point, and PV2. In this case, we want to access the neighbors again. Want to access their position, so let's grab their position and 2. And we say that if it is a neighbor with the same point position, we say that it's a new position. So let's make this variable vector new position, because we want to put the whole roof down. Like all the top points, they have to go down to be on the same line with the merging roof. So we want to set it to 0 minus distance 2 and 0, because we're going to subtract. And we say that set point attribute to set this neighbor and 2 new pos. I want to say add. And we want to say that our py is also subtracted by the distance 2, and it is a ray point. So here we want to say that bring down the top neighbor as well. Yeah, if the merging is of the same direction. Yeah. So apply that. And oops. And if there is no intersection, make a side. By which I mean a platform, but we already taken this name platform to make the height value, so this one we will call it the side. So else if inter 3, like if there is an intersection with the wall, we also want to say it's array point to number 1. Array point 1. But regardless of whether this intersection is true or not, we want to make the side. So let's say we need a side primitive. We say it's add primitive 0 and poly. And we want to set this primitive attribute to a side. That means that it's a side, but that's side primitive, and it's 1, which means it's true because our side attribute is going to be a boolean, and which reminds me we still need to create it because we haven't created it yet. So actually let's do it right away right now. We want to say that let's do it outside of this loop, and here we will attribute inside here, and we want to say that attribute create, and yeah, we want the roof extrusion, and it's called attribute side. It's a primitive side, and it's an integer. Yes, good. And here apply. We also want to say that we want to add vertex to our primitive, because right now it just you won't even see it. We want to add it in our index 1 to our side primitive, and we want to add our point number. And not only we want to add the point number, but we want to add it to all of our neighbors that are bottom ones, because this is the side of the roof, and this is like what is going to close the roof. And the platform we're going to do in a second in another node, but first let's finish this. So it's again we will access our neighbors, and again we will grab the position attribute and 2, and we say that if position y is not equal to p.y, this is our guy. So this is the one we need to add the vertex. Side primitive and 2. So apply accept. So that is the side. So what happens is, if our points never intersected with anything, and they also did not intersect with the wall, because if there is a wall we will never see this side, then it looks for the bottom points and it creates a primitive out of all 3 of them. And this point, since it found its neighbor, it found that it can actually intersect with someone, it goes here. It moved. So let's see what we have. Oh yeah, we're only doing it once right now, so okay, never mind. Now, after that is done, we want to create a platform. In this case, we don't have any platform, because this roof is just rests on the bottom. So let's go up. Let's find a case that has a platform. I think this one has number 3. So grab this. So 3 and 3. Yeah, it has closed sides on both sides. And yeah, because it doesn't intersect with the wall, and it should have a platform, which is good. So let's make one. So for that we need to grab our initial primitives that were not cut yet, and we want to grab the same number as the current loop number. So copy this stamp, bring the stamp, say primitive delete non-selected, and what you don't like something, is it a valid group? Oh yeah, we got the brackets. So here you go, and let's click this one. It pins this view, then it will be updated correctly. Yes, and here we just simply want to extrude it. So let's bring poly extrude, and we want to extrude it to our platform number. So we want to grab the primitive attribute from the input of first index, from the first primitive number, and it's called platform 0. So here we go, our platform. And we also want to make a switch but sometimes maybe the platform does not exist and we don't want to fully extrude anything. And we want to say that, +1, so let's call it locate platform. Yeah, so we want to ask it whether the locate platform prim locate platform 0 platform 0 is equals to 0, and it is not. That means that's all good. We want to merge it with our loop here. However, as you might probably notice, our sides, at least this one, does not have the correct face normal, which will be a problem later on. So we need to make like an additional check. So we need to isolate sides and non-sides. So sides, and this one is no sides, and we want to say that if side is equal to 0, this one no sides, delete non-selected, yes. And this one is, let's copy, paste it here. And here we only want the sides. So yes, as you can see, this one doesn't point to the correct direction, like though it's point normals point in the correct one, face doesn't, because face determines by the direction in which it was created, like in vertex direction, whether it's clockwise or not clockwise. So it's a very easy check. So we just need another attribute wrangle. Yes. We want to name it check primitive normal. What we will do is we just, like a very small cute trick is just we want to bring facet and we want to post compute normals. And as you can see, it will compute the normals of the points according to the face. So we will call it normals according to primitive. However, this will be an indication that something is wrong because the results of these two, they differ. So that is that will be like our driver, whether we need to check this stuff. So here, let me bring it bigger. So what we want to do is we want, of course, bring out points. So prim points, the whole array of them, prim num. And we want to grab two vectors. We want to grab normal after, so point normal after we modified it, so 1 and PTS 0, which is going to check only 1 point, and vector and before, so the same but from the first input, index 0. And we say if and after is not equals to and before, so their normal was modified when we put it through facet node. We want to say remove the prim because it wasn't correct one. Say remove it. Do not remove the points. It's very important, so we need them. And we just create a new primitive. Add prim 0 dot, and it's a poly one. You can also say polyline, and we'll just create a line, but in this case we need a poly. Oops. And we say rewind the vertex order because we're gonna create this face in an opposite direction, opposite count, so to say. So we say for int x, and x will actually be starting from the last point. X should be bigger or equal to 0, and x is minus minus, so every time it will go 1 down. And this is how we're going to add the vertices. 0 to our new primitive, we're going to add the PTS of x. Apply. And something is wrong, new new PR here. Apply, accept, new PR. Okay, just a bit slow today, guess. So side, no sides, check. And as you can see, bravo, all correct. We just reversed the direction of, not even the direction, but sequence of the vertex numbers. So yeah, that is our small check. And here we are, to merge. So let's go up, new, and let's say do it for all of them. So from 0 to n prims in our second input, because that's where all non-modified and non-clipped faces are. And yeah, and that is our roof. Very nice. So let me go up again so we can merge it with our body, and let me unpin this view. And let's check other cases. So let me check other seats. Yes, all good. And as you can see, everything works perfectly. Yep. Very nice. So let's go back to our seat that we chose, 248, I think it was. No? Oh, yes, this is the one. Very nice. So that's it for this part, and I would think that's it for this chapter, because that is our base. That is the base that we're going to treat, and we're going to set dress and make it look very pretty with all the beautiful shaders and modules and complex, well, not complex, it will be complex looking, but it's in essence very simple geometry, where we're going to utilize both generated elements as well as the pre-made ones, which I'm going to include to the file, so you can just use those, or you can make your own, also a possibility. So thank you very much for watching, and I'll see you in the next video. So while looking for the appropriate seat, I found multiple issues in our roof base, so let's just fix those quickly. If you go to the roof attributes, what you need to do is put an area, and type area. It's a measure node, put it on area, and in get middle line, you want to add another attribute transfer, and you want to transfer from the original area that is connected to the second input, and you just want to locate by stamp. You just need to transfer the area to the middle line. And in roof direction, you want to transfer this area to the points attribute. So why do we need this area? The answer is quite simple, because in our in and out attributes, when the roof is checked, for example, the roof number 1, let's make it number 1, is being checked, and it sees this middle line that belongs to this big, to this big roof. It sees it as incoming because it touches, like this line touches our roof. However, in incoming, we will need to write a couple of additional lines. In while loop, where we import all the attributes, we also want to import the area. We want to create a variable for it called roof area import. As well, if you want to create another variable, original area. Original area is the area of the primitive that we are checking. So you want those two. So once you imported the area from the middle line, as well as you have the origin area, you want to check if the roof is of the same direction. The way we want to do it is first check whether there is a direction. So you need to check whether there are any points in a second index, because our second index is a midline of the primitive we're checking. So if that is true, you want to know the direction. It's also very easy, just a normalized version, and you just subtract 2 points of this line. So for index 2, point number 0 and point number 1, just subtract their positions and normalize it and call it origin direction. And you check in if absolute of round version of roof direction import is the same as absolute and rounded origin direction. So if they're the same direction, if they are indeed the same, then you want to compare the areas. So you say if origin area, the area of the primitive we're checking, is smaller than the area of the import, that means it is not an incoming, because the roof that is incoming with this the same direction is actually bigger than our roof. Therefore, it cannot be an incoming. You want to say the same direction check is 1. I created this in here. It's an integer, just a boolean, and it is 1. And where you append the incoming to our list, make sure to add a condition only if the same direction check is 0. So if that is true, if the area is smaller, that is not an incoming roof. And don't forget to zero out the check for the future loops. That is one thing. So that is fixed. And once you fix that, I will bring 0 and in here. So once you fix that, in the roof extrusion, it was just a small mistypo by me. in roof extrusion, not roof extrusion, in roof merchant sites, in normals and ray. If you go all the way down to where we brought down the top neighbor as well as the merging is of the same direction, make sure to put this outside of the for each loop. Without realization, I wrote it inside the loop and that's why it didn't work. So make sure it is outside of the for each loop, but it is inside in our if condition. So yeah, so that is it. That is all you have to check. And after that is done and delete it, everything is good.